camera and mic stayed on this time. I just like pause for a second just to see if my camera and mic gets shut off every time I start recording. Right. Welcome to office hours part 2, I guess, for this week. Hope everybody's had a good weekend. We will be going over the remaining material for exam 2. I did make some slides so that I can talk about a few sort of tips and things I think you should focus on and things I think you should prepare for. So I'm going to do that first, and then I will go into the remaining practice problems that we didn't get to do yesterday. All right. As always, we will be recording this session, making it available for the rest of the class. So if you plan to speak or type in chat, just be aware of that. Exam 2 layout will be, like I said yesterday, 2 graph algorithm design questions, a set of multiple choice questions. Each section will be worth 20 points and for a total of 60 points. So it's a pretty standard exam. I think the only exam that's kind of different than the other ones is the first one, where we have 3 problems because we have to split dynamic programming to 2 problems. I think this exam and the next exam, you should be expecting 2 design questions or 2 written questions, and then the rest will be multiple choice. That's of course subject to change, so don't say, oh, Joves said this, so you can't make any changes. How the exam is constructed is entirely up to Dr. Bretto, so he can on a whim do anything he wants. A funny story about this, if anybody wants to talk, ask me in chat, I'll tell you a funny story where me and a different TA pranked Jamie during this semester. He was a student. That was pretty funny. So graph solutions, you've seen this slide before, so I won't hold on to stay on this for too long, but you have to make sure you write your algorithm and then your justification of correctness, and you have to make sure you have all parts. Algorithm, no pseudocode, state your black boxes, do not modify your black boxes, detail your input and output modifications, detail any data or return extractions if you needed. Write as much as you think will make the solution clear. It's always really painful for you to be like, oh yeah, I definitely meant this, and then you didn't write enough for the TA to understand what you mean. So if you have any doubts about whether the TA will read a part of your solution correctly, just add a little bit more detail, add some notes, that also helps. So keep that in mind. Why did you pick the black box? What modifications should you make to the inputs and outputs? Why did you make those inputs, make those modifications to inputs and outputs? And why does your return value solve the problem? And then runtime analysis. Go ahead and insert the known runtimes of any black boxes. Make sure you talk about any input or output modifications or any data extraction. Should be in terms of N and or M. And we have started saying that if you have a black box runtime and your graph is in such a way that you could simplify that runtime, you do not need to simplify that runtime. So if you give us Dijkstra's runtime, regardless of whether the graph is connected or not, we will take Dijkstra's runtime as is. You don't need to simplify that. So keep that in mind. But if you do just something like run 2 Dijkstra's, right? You can't have 2x Dijkstra's runtime. You do want to simplify that because that is just the flat runtime of Dijkstra's. Okay. Graph algorithms. Read the list of black boxes post very carefully. Treat the algorithms as a black box. Do not modify. Consider inputs, outputs. Chain black boxes if you need to. I think I've done a few of those with the practice problems. And the challenge of this whole thing is to frame your problem as a graph and then manipulate your graph so that it solves your problem. Selecting the right black box based on the input and output needs, and then justifying correctness and runtimes. And this is a form of reduction. We will see more reductions in the next topic, but this is considered a reduction problem. Graph properties. These you really, really want to understand because they help you with, they give you a clue as to which black boxes you need. So directed versus undirected graphs, weighted versus unweighted graphs, connected components only make sense in the context of undirected graphs. Similarly, strongly connected components only make sense under the context of directed graphs. Sources and sinks only exist in directed graphs. you wouldn't have a start or finish with a graph that has no direction, right? Cycles can exist in both types of graphs. Bridges, I went over what bridges are in, I think, the very first office hours. I'll go look at that if you don't understand what bridges are, what leaves are, what a DAG is. These properties are all very important to understand and be able to read and immediately recognize what kind of graph that is. Common mistakes that I went over. Don't want to stay on this for too long, but yeah, these are all the common graph mistakes. Pause here so you can take a screenshot or look at it in the replay if you need to. And then, but this, I go over each of these specifically, I think, in the first office hours. And then MSC common mistakes, I did this, I think, in the second office hours. So make sure you don't accidentally do any of these during the exam. Okay. Specific posts that you should read, reread, and make sure you fully understand. These are very important, okay? Common course runtimes. We added the graph runtimes, I think, when the graph topic started. So if you haven't looked back on that post, make sure you go find it. Learn about all the runtimes for graph operations, graph theory guidance. This is how you write the solution to a graph theory question. So make sure you review that post. The usable black boxes are super important. You need to memorize and know all of these. You should know what the inputs are, the outputs are, and the runtimes are. Because when you go and you solve your problem, you're going to use one of these black boxes. And if you forget how the black box works or what the input and output is, you're going to be in trouble. So memorize all these black boxes. Go look at the Ford Fulkerson example that Emily has posted. It's super helpful to kind of walk through those steps and understand what the steps are to finding a max flow. Homework assigned problems, go read them, go see what other students' ideas are, even if it's not the solution you came up with. If a different idea or different solution also works, it's good to have that kind of context and that perspective. Also, go look at the feedback threads. Like I said, if you haven't made a mistake because you've been doing really well on your homeworks, you may not know that a mistake like that can be made. And if you make that on the exam for the first time, it's going to be really bad. The other thing is, if you haven't done any homework, you're already falling behind, but don't make it worse by not going to see what the solution of those homework problems are. Make sure you go look at those threads. The practice problems are also important. So the practice problems that we have given you model solutions for, make sure you go read those threads, see what anybody has talked about or asked questions about. Make sure you fully understand those questions. And then the suggested practice problems, if you want to further expand on your practice. General exam advice by Asia is super helpful. Go read that. And if you did not do well on the first exam, or even if you did do well on the first exam and you're wondering, what can I do to improve on my second exam, or what can I do to continue my success in the second exam, go read the troubleshooting study practices. Asia has put a ton of time into writing these posts. They have been super helpful for students that have struggled in the past. So if you are looking for advice, go read those posts from Asia. Exam proctoring and logistics. I know that this sounds silly, but even though you've taken the first exam and you've gone through your proctoring and you did fine, students will sometimes forget going into exam 2 that our proctoring rules and requirements are pretty strict in this class, and they'll forget to do something on the second exam that ends up getting penalized or a disqualification of the exam. So go reread those exam proctoring and logistics, redo the onboarding exam if you want to just kind of remember what the process is right before the exam. That's fine. So make sure you remember that. Okay. General things that I think you should know going into the exam: how to solve every single homework problem that we have had on this topic. If you haven't done them, go do them. If you did it and didn't do a good job, go try them again. If you did it and you got a really good score, try them again anyways. These are the problems that will be used that you should focus on going into the exam. How to answer all the content and format quizzes. If you didn't get full points on those, go back and look at those quizzes. Go and understand what the question is asking. The format quizzes is super important because you want to write your solution correctly, not just be able to solve the problem, you want to be able to properly present your solution to the TA that's grading. Runtime of all graph operations. So how to update an edge way, to remove an edge, to remove a vertex, to add a vertex, to add an edge, to delete all edges that fit a certain requirement. Go read up on that and learn what the runtimes for those are. All your black boxes and their strategies. So I list out what strategies you should consider on all black boxes whenever I do office hours in the first one and second one. If you haven't seen them, go take a look and keep that in mind going into the exam. Black graph properties and what black boxes they allow. So I talked about this earlier. You need to be able to recognize when a graph is undirected and has a weight, what algorithms care about that. If a graph is directed and unweighted, what algorithms care about that. If a graph has negative edges, what graph algorithms allow for that. So keep that all in mind. Go learn that. Tree properties and how they interact. So that was, I believe, the second office hour for this topic. So go and learn all the tree properties, the n-1 property, the unique path between all vertices within the MST. So all those properties you should know because they'll help you with solving MST problems, and they'll also help you with any multiple choice questions. Know what the cut property is, know what the cycle property is, the ST cut, what that means, how to draw it, how to figure it out, what the max flow min cut theorem is, how they interact with all the flows and all the cuts within the max flow problem, and how the min cut is the max flow equals min cut for a given flow network. These are some toy examples I like to use when I solve graph problems. I'll go over each of them. You can make up your own. You don't have to use these, but some students have asked me, like, how do you run your algorithm through? So these are just some simple ones. So this one right here is a it's a DAG, right? So A goes to B and C goes to B, and there's no cycle here. So this is a DAG that I like to use for like a really simple directed graph algorithm that I'm working on. This right here is a 3-vertex cycle. This is the smallest cycle you can have on a simple graph. And so when I am working with cycles, I start with this, and then I will make another one that has more cycles. But this is the first one I start with. This is a straight path. You want the last one? Here you go. I'll give you 5 seconds. All right. This is just a straight path. It's really simple. Sometimes when I'm working with DAGs, or when I'm working with, I have an algorithm that I need to know about sources and sinks, I'll just draw a straight line and work with that. This one's a little bit funky. You don't have to memorize this. What's useful about this is that there's 2 sources, there's 2 sinks, and there's a fork in the middle. Okay. And so whenever I come up with like any sort of SCC type algorithm or any algorithm that works on a DAG, and I don't want to make any bad assumptions, like, oh, assuming there's only one source, assuming there's only one sink, assuming that you have a path from beginning to end, if you only have one source and one sink, this is the graph that I have in my mind that I just go, oh, right, like even if I have a single source and a single sink, I don't have a path from source to sink if I have a fork, right? So this is how I visualize those type of requirements. This is just a little diamond that I like to use. This is the graph that comes to my mind when I think one of the MST questions was, can the unique lightest edge, is the unique lightest edge always in every MST? And the answer is no, because I know that this double cycle sharing one single edge graph exists. And so I know that if this is a 1 and this is a 1, and say this is a 4, right? And then this is a 5 and this is a 5, right? That if this edge is the unique lightest edge of this cycle, it's also the unique heaviest edge of this cycle. And so therefore, this edge cannot be part of an MST. So visualizing this gets me that. I like this graph right here because it gives me a bridge. It's a single cycle with a single bridge. So any sort of algorithm that might be dealing with a cycle, might be dealing with a bridge, or might be dealing with both, I like to visualize this one. I like to use these two. Basically, the A to D is the shortest path. using this edge, whereas A, B, B, C, and C, D here is a longer path, okay? But if I was to do a negative, A to D is not the shortest path. This -3 path from A to B to C to D is the shortest path. And this helps me visualize anytime I try to do something that's like Dijkstra related, or graph related that has negative edges. Can I do something with it? And this always tells me that I can't use Dijkstra, and it always tells me that I can't just shift the edges because it doesn't work with this specific example. So these are my toy examples. Use them if you like. If not, come up with toy examples and then just use them on the exam. Okay. General studying tips. So this goes over the same studying tips I had for exam 1, but it's worth repeating if you forget, or if you didn't hear them for the first exam. So don't cram it all into one night. This class is notorious for being very difficult for the topics and subjects to sort of like it needs to soak in your brain. So you have until Sunday to take the exam, right? You still have a good week. So if you haven't been studying, start studying today. Start studying today and start absorbing that material that you need. Because if you do it all on Saturday, you're not going to be able to absorb enough of that information on Sunday. It is very, very difficult. And quite honestly, if you can study on Saturday and ace the exam on Sunday, you're already able to ace this class regardless of your studying habits. So, but if you can't do that, then I suggest you start studying right now. Work out a schedule and stick to it. It's really easy for you to be like, oh, I didn't get to my 2 hours today. I'll just do 3 hours tomorrow. Oh, I didn't get 3 hours in tomorrow. I'll just get 4 hours the next day. It just stacks up by pushing everything off. So I just suggest make a schedule, say how many hours you want to study or how many topics you want to cover, and just do it. Okay? Do the assigned homeworks again, those that are graded. Do the assigned practice problems, those with official solutions, and then do the suggested practice problems, those that don't have official solutions, right? So these are my tiered choices of what priority I would give these. Okay, and then focus on the ones that's most similar to homeworks. There are going to be some questions like how do you walk through DFFs? How do you walk through Dijkstra's? How do you walk through Kruskal's, and how do you walk through PRIMs? And those are important in terms of like understanding how those algorithms work, but you're not going to be asked something like that on the exam. You're not going to be asked, to walk through that by not by a lot. It's not going to be like, here's a graph, do the entire DFS tree. It might be like, oh, if I was at this position, what is my next my next post number or pre number? Like it'll be a very isolated question. It won't be like walk through a whole graph. Okay, that is really, really time consuming, really, really error prone, and it doesn't tell us anything about your mastery of this topic. All right. Don't spend too much time on the harder problems unless you have done studying and you're really interested and you want to get a big picture. They're meant to stretch your abilities. I didn't really attempt them until after I became a TA. So if you're really good at the topics and you want to try them, go ahead. But don't spend hours on it trying to figure it out. If that's the case, then just move on. Take breaks if you need to. Let the subconscious of your brain absorb the material that you've already gone over. It's good study practice to not just stare at the problem for hours on end. Your brain needs rest, and your brain can continue working without you staring at the problem. Go take a shower. Go watch some TV. Go relax for a little bit. Try to study in the same environment you will be taking the exam. So if you plan to take the exam at 7 p.m., study around 7 p.m. If you plan on taking the exam in the kitchen, clear out your kitchen and try studying there. It's really, really helpful for your brain to be triggered by the environment that you were studying. It tries to recall that feeling. It tries to recall, it tries to recall the last time it was in that situation, what you learned from it. And these are all like, known studies on best study habits. I'm not just making these up. Try to study in the same environment that you want to take the exam. Around the time that you want to take the exam. Study with others if you prefer, but solve the problems yourself. A lot of students will have this like false sense of confidence where, oh, I solved it with my 3 group mates, And because we were able to come up with an answer, that means that when I go take the exam, I will become able to come up with the answer. That's a false sense of confidence that you can instill in yourself, and you'll move on to the next topic without fully understanding the one you're at right now. So I do think studying with others is super, super helpful, especially when you're the one that's teaching them the material. But do solve the problem yourself first so that you know what your limitations are. And then my super pro tip is to go to the regrade threads and try to see what mistakes other students have made. I talk about this all the time. Other TAs have as well. Learning other people's mistakes helps you avoid them. Okay. And then, yeah, if you haven't submitted a solution, which is already a terrible, terrible idea, go read those threads. Ravi, I see your hand up. I'm going to finish the tips, and then I'll see the question you have. For the actual exam, what you should do prior to the exam, you should rest before the exam. Don't tire yourself out going into the exam. Your mental capacity, your mental state has a lot to do with the success of this exam, especially since it's a really long exam. So if you go into it tired, you're going to be exhausted midway through the exam, and you're not going to be able to perform as well. Try to be relaxed. I know that's really, really hard, and I know it's easy for me to say because I'm not the one taking the exam, but if you go in there really, really anxious, it can only hurt. You want to go in there confident and as relaxed as you can. Do some yoga, do some meditation, watch a sports game right before, right? Do whatever it is that you normally relax right before your exam. Slow down. Don't blaze through the test thinking, oh, you're going to run out of time. Go through it at a nice pace to make yourself feel like, okay, you have plenty of time to do this. You have you should focus on the current question. You should read it fully. You should make sure you understand the questions, okay? Students suggested watch Georgia Tech football before your exam. That might help. I think we have it. I think the next opponent is pretty weak. I think we actually have a really easy schedule, so chances are we'll win. But if we lose to like a really easy opponent, you're going to be devastated. I know I will be. So maybe that's not as safe as you think. So I read the problem, read it again, and then again. Make sure you fully understand the problem. What I like to do is I like to write down the problem and its properties to make sure I know all the graph has given me. I'd like to write it myself because when I read it, my brain will say, oh, you've read this, but your brain has a way of like just glossing over details because it gets the general gist. So make sure you write it. When you write it, your brain has to acknowledge the words that you are reading in order for you to copy it and paste it onto a piece of paper. So I like to write down the actual problem. I say this, but we have recently changed the way our multiple choice questions are created. They are done in sort of a question bank. So students get similar questions or questions on this similar category of similar difficulty, but they're not exactly the same. So you should still write it down just so you can compare notes with other students, because there are going to be students that get the same questions. It is a big question bank, but it's not unlimited. It's not so big that every student will have questions dedicated to them. That would be kind of cool. But yeah, write down your multiple choice questions and answers just so that you can compare them with other students. Don't select the right multiple choice question answer. Eliminate the wrong answers. There are going to be times when you read the list of answers and the first one will sound really good and then you'll answer and you'll move on. But the second one's going to sound even better, or the third one's going to be like the perfect answer. So just read them all and eliminate the wrong ones before you move on to the next question. And again, I personally like to answer the multiple choice questions first. I like to read the written problems and then move on to the multiple choice questions so that I know exactly how much time I have left when I go to the written part of it. If I do the written part first and I start to have less and less time, I don't know how much time I have to solve the multiple choice questions, and multiple choice questions do not have partial credit, whereas the written parts do. Okay, and try to enjoy the exam. Seriously, this is the advice I give all students, because if this is your last class and you don't plan on getting a doctorate or another degree after this, this could be the second to last exam you ever take. And so don't make it a miserable event going into it thinking this is going to be a miserable exam. Just try to enjoy it. I remember my final 3 exams at Georgia Tech very fondly. So hopefully you do too. All right, Ravi, you have a question?
Yes, Joves. I want to go back to a previous slide. Can you do that, please? I want to ask a question about that.
Yep.
Okay. Here's the thing, Joves. At this moment, I understand the homeworks 5, 6, 7, 8 graded problems. I can write down the algorithm in this case, the algorithm, the most optimal solution, the justification, and the runtime analysis. In fact, I did really well on the homework 5. I know for a fact the other 3 homeworks haven't come yet. But while I also understand the assigned practice problems, the ones that you guys gave official solutions to, I've been struggling heavily with the suggested practice problems, the one where you wrote down 3. Is that going to be a big problem? Because I've been struggling a lot with these really hard practice problems, and I'm concerned that's going to be a huge detriment to me. Do you understand that, Joves?
Of course, I understand struggling with problems in this class. I struggle with problems in this class. I would say that if you have number 1 and 2 like very solid foundation on it, you are in a pretty good state going to exam. I think the suggested practice problems, some of them are purposely more difficult than you would be possibly see on the exam. They are not meant to be like, oh, if you aren't able to solve these problems, you are going to fail the exam. They're meant to sort of like push you beyond a comfort level, maybe even beyond your limits on some of the problems. I think it would be a problem if you couldn't solve any of them, but if you can solve, a handful of them, or at least understand the solutions that I presented, I think it'll be okay. I don't think you have to be able to solve every single one. Even now, when if I was to see one of these problems that as if I've never seen them before, it might take me some time to solve those problems.
Right, because here's the thing, Jovis. I've been the way I've been approaching the problems was that I've been like trying to solve the problems without looking at anyone else's solutions, whether it be on Ed
That's a good start.
Sorry?
Yep. That's a good start. Yeah, I agree with that.
But that's where I struggled. I never used the AI or anybody else's solutions, and that's where I struggled. I try to work it out on my own, and that's why I'm telling you all this.
Yeah, and that's fine. I mean, there is going to be a point where like you just can't solve the problem because you've never seen anything like it. You've never seen a approach that would teach you how to solve that problem. So what I would suggest is you should struggle on these problems for a little bit, and if it comes to the point where like you just can't solve it, go ahead and watch the office hours or go ahead and look up the solution. Understand that solution, understand the explanation of that question, and then come back to it later. Come back to it later and say, okay, now this problem, I've seen what the solution should be. If I reapproach this problem, having learned that, can I solve this problem? If not, look up the solution again and then move on and then come back to it again. Keep doing that until you can come back to a problem and go, oh yeah, I know how to solve this problem. The knowledge you gain from other people, from other solutions, from online solutions, from my solutions, is still your knowledge. It's not knowledge that you're just like, oh, it's not my solution because I had to go learn from it. If you just stop at that, yeah, you're not really getting much out of it. But if you come back to the problem and you're able to solve it, then that's good. That's fine.
Okay, and second thing, and I'll let the other guys go. When you're writing your algorithm and the algorithmic response problems, like the 2 that we're going to answer in the second exam, we must not only write down the correct answer, but we must write down the optimal solution, correct? The one with the most optimal runtime. Otherwise, we're going to lose more than 8 points, and that's going to be a huge disaster, correct?
I don't know the point values of a suboptimal solution on the second exam. That's a grading rubric question, so I'm not going to say how many points you'll lose. I will say that if you write a working solution that is not optimal, you will lose points. How many points depends on what the grading team decides to allocate.
Yeah, that's what I mean, right? We had a problem with that in the first exam, so we want to make sure we never do this again. So that's why I'm asking, like, we must not only write down the correct solution that works, but we must write down the most optimal solution, one that
Okay.
attains the most optimal.
I want to make it clear that I feel like the way you are wording the question made it seem like you were not made aware of this. On the question itself, I believe Dr. Britta always says correct and fastest solutions will get more points or something to
Okay.
that effect. Like it is very clear on the question in this class that an optimal solution is one of the requirements to get full points.
Okay,
or
thanks.
at least a solution that meets our target runtimes.
Okay, thanks.
Yep. Linton?
Sorry, I was on mute. So I just want to find out because I only have the slides shared in the chat window. I don't know which question you is kind of related to the one we can maybe save a skip before the exam. Then I can come back if I'm interested in knowing more details. Is this a list you gave to us for the practice questions?
Oh, the list is posted in there's a list of additional practice problems for both graphs and MST and max flow. So the graph questions I went over last week. I went through all of them, or all of them except for the one that's like, walk through this algorithm. I don't find those to be particularly interesting. And then today I'll go over the MST and max flow problems that was set as practice problems.
Okay, thank you. I will find out later.
Yep.
Thanks.
Yep. Jafar?
Yep. Hello. So thank you for the session. I have only a small question. So in the general things you should know, there is the cycle property.
Yes.
Cycle property as cycles, or there's a property somewhere that I'm missing?
This one?
Yeah, this one.
So I went over this, I think, the second office hours for this topic, and I also showed a few problems that uses the cycle, or I talked about a few problems that uses the cycle property. So that's the statement is that the unique heaviest edge of a cycle cannot be in any MSD.
Okay. Yeah, this is something that I know already. But this is the cycle, the normal cycle. There is no property or something like we don't know. We need to know.
That's what the cycle property is.
Okay.
Like you don't
okay,
need to know it. It's really helpful for like,
Yeah.
and when you want to come up with an algorithm or come up with a answer to a multiple choice question.
Definitely. Yeah. Thank you.
Yep. All right. Let us move on to one more question. Manjunatha?
Joes, a question on that particular toy example that you had where there is a unique heaviest weight edge. Can we use the cycle property in that case to pick up the lightest edge? Like, can the cycle property work in that toy example? You had, if you can go to a toy example window, there is one particular example where you had a diamond shape with one middle edge with 4. That is the lightest for one part of the, here, please. Yeah. So in this case, the cycle property would work because the quiz question was, can that middle edge be part of any of the MST, or it will be always part of the MST, or drop part of the MST, I guess. So if you use a cycle property, then if you go from B, then that edge will be dropped. But if you go from D, that will be picked.
So the statement that was made on the problem was, is the unique lightest edge of a cycle always part of an MST? And the answer is no. And this is the example that makes it no. Because the unique lightest edge of a cycle, if that edge is also the unique heaviest edge of another cycle, it cannot be part of the MSD. That's what the cycle property tells us. So in this case, 4 will not be part of any MST at all.
Okay, so it has to consider both the cycles.
Yes.
Okay,
Well, you have to. I mean, the first statement that I made is just false. I'm letting you know that that is not a true statement. So the only thing that matters here right now is using the cycle property. We know that this is not a part of the MST because it's a unique heaviest edge within this cycle. Whether it's the lightest edge of this cycle or not does not matter. It's just completely eliminated by the cycle property.
Thank you.
Yep. All right. Time to move on to practice problems. Five point five. Consider the undirected graph G with non-negative edge weights W greater than or equal to 0. Okay, so we have no negative edge weights and we have an undirected graph. Suppose that you have computed a minimum spanning tree G and that you have also computed shortest path to all nodes from a particular node S. Okay. Does the minimum spanning tree? Okay, so if we edge weights is increased by 1, the new weights are, okay, so we've increased 1 for all edge weights. And we have the MST and we have the shortest path. So the question is, does the minimum spanning tree change? Give an example where it changes or prove it cannot change. Okay. And then the second question is, does the shortest path change? Give an example where they change or prove they cannot. So the answer to the first part is that it, anybody want to guess at what the first part is? Whether the spinning tree, the MST will change after we add 1 to every single edge. We have 1 no. We have 1 yes. Okay. 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 So the answer is no. And you can kind of, without actually having to like write down anything that's like super proof B, consider that when you sort a bunch of edges, right? And Chris goes through and picks those edges and it checks to see if it creates a cycle or not. If you add 1 to every single number in those sorted edges, it does not change the sort order, right? So it will still consider the edges in the exact same order that it would have on if it was the original order versus the order of the edges plus 1, right? So that does not change. And then the second one, we talked about this before, is that it does change, right? I've given you examples of how this changes because if you have if you're looking for a shortest path and you change the weights of every single edge, it disproportionately affects any path that has a lot of edges versus any path that has very few edges. So you could potentially take a path that has a lot of edges that used to be the shortest path, add 1 times however many edges that path was taking, and then you could potentially overtake another path that only uses 1 edge that only gets plus 1 to it, right? So the first answer is no, and the second answer is yes. Here's what I wrote. Since all edges increase by 1, the sorting of the edges does not change, and the lightest edge across a cut that does not create a cycle will remain the same at each step of an MST algorithm. The second part is yes. Suppose the shortest path from S to U is over X edges with a weight of 1. If there exists some edge with a weight of X plus 1, so right, we have a a path with x and a path with x plus 1, then if we increase all edges by 1, the previous shortest path from S to U is now 2 times x, right? It takes twice as many, it costs twice as many to take that those x edges, okay? Whereas the other path only adds plus 1 to it because it's a single edge, right? So for some x and x plus 2 is going to be less than 2x, right? And it's actually mostly true for any x, right? Especially if these are positive edge weights. So it's no and then yes. Okay. Any questions about what problem is this? 5.5? Nicholas?
This is kind of on the first part because it came up on the ed thread about this. So Chris calls, I know it sorts it by edge length, but if they're non-distinct, there's some tie breaking there where you can have multiple MSTs that are the same size, but different shapes. Should we assume that if you run Chris calls on a tree multiple or on a graph multiple times, you would get the same tree every time?
So that's not, you shouldn't assume that, but that's not quite what the question is asking. The question is saying you already have an MST. It is a valid MST. If I add 1 to every single edge, does that no longer become an MST? Do I have to fix this MST that you already have? And the answer is no, you don't have to, because it is still an MST. It doesn't change the fact that it's an MST.
Got it. I see that now. Thanks.
Oh, okay. Cool. 5.6. Right. Let G be an undirected graph. Prove that if all its edge weights are distinct, then it has a unique MST. I like this one. We wouldn't require you to like come up with a very math heavy proof. So I just came up with like a way that I thought allowed me to argue it. But one way to argue it would be that, you know, if you were to run Chris Gauls, no matter, you know, no matter what order you give these edges to Chris Gauls, it would always choose the same sort because they're distinct, and Chris Gauls would always use the exact same order to pick those edges. Another way to argue this is by contradiction, which is one of my favorite ways of arguing these types of things. So suppose we have two MSTs. Okay, so let's pretend for a second that we have two different MSTs. Okay. So that means that at least one edge, E1, right? Some edge that's in the first MST is not in the second MST, right? Because if you and you can add it from the first MST to the second MST to create a cycle, right? Because they're different MSTs, I have some edge that's going to be different, right? And then we take E2 that's in this cycle, but not in T1, right? Because we will create some cycle. And because we have created some cycle, there must be an edge within that cycle that wasn't in T1 because they're two different MSTs. So that edge cannot be in the first MST, right? So now we're going to compare these two edges. Let's say this happens and we compare the edges, right? So E1 cannot be the same weight as E2 because all weights are distinct, right? We can make that argument. So one edge that's in the first MST that's not in the second MST cannot be equal to any edges in the second MST. So now we have two situations, right? If E1 is less than E2, then T2 can replace E2 with E1 and get a smaller weight. So T2 cannot be an MST. If T2 can remove one of its edges and improve its weight with a different edge, it was never an MST to begin with, okay? Similarly, if E1 is greater than E2, then T1 can replace E1 with E2 and get a smaller weight. So T1 cannot be an MST. So, right? So if I could improve the first MST, the first MST was never an MST to begin with, right? So because of these conditions and this contradiction, saying that, you know, oh, if I swap the two edges, I can improve one of them, which I can't because they're both MSTs. And therefore, there are no edges that I can take from one MST to put into the other. that wasn't originally in the other MST. And so because of that contradiction, both of those MSTs must be exactly the same because they all have distinct edge weights. Okay, and that's the proof by contradiction of why this is true. Mahmoud? Okay.
Can you hear me?
Yes.
Yeah, sorry. So when we were talking about crystals, you said that
you have
the
an
source
echo,
of
or someone has an echo with you. Does anybody else have their mic on?
Sorry. I
Okay.
don't know why I was doing that. I had to turn off something on my phone. It's my first time doing Teams on phone. Sorry. So the crystals, it does sorting, and because of that, it's always going to be in the same order, regardless. Everything is unique. What's the logic of prims? I'm struggling to figure out how to like word it for prims.
So prims is going to pick the lightest edge from what is already part of the MST and what is not part of the MST. And because your edges are going to be distinct, the lightest edge under any configuration will always be the same edge that gets picked. But that's a much harder way to explain it. I wouldn't try to explain it that way. I like the one with crystals because you can just say, oh, no matter what order I put my edges in, crystals is going to draw me the same MST. It's a little bit harder to argue with prims. So, but this proof right here that I have with contradiction doesn't require you to know what the algorithm does.
Understood. I just wanted to kind of figure out the logic for prims, just so I can wrap my head around it. Thank you.
Yep. All right. So next question is 5.7. So this is asking for the maximum MST. Give me 1 second. Okay, so we're looking for the maximum spanning tree of a graph that is the spanning tree of largest total weight. Okay, and so we can do this by simply inverting our edge weights so that anything that used to be a really light edge becomes a really heavy edge, and anything that used to be a really heavy edge becomes a very light wedge. And therefore, all the heaviest edges now being very light wedges, edges will be picked for the maximum spanning tree. All right, so step one, we are going to create a new set of weights such that W prime is equal to the negative of every single weight. That is that every weight in W is multiplied by -1 to get the weight in W prime. Okay, we call Kruskal's MST algorithm on this, and then we get back the maximum, the edges that is the maximum spanning tree, such that E max ST are the edges for both the minimum spanning tree of G and W prime and the maximum spanning tree of G and W. Okay, we return this maximum spanning tree of G. And the reason this works is that by negating all edges in G, we have inverted the weights of edges in G such that the lightest edges are now the heaviest edges, and the heaviest edges are now the lightest. Then when we run Kruskal's, it gives the minimum spanning tree of this new of these new weights, which is actually the maximum spanning tree of the original graph. Okay, so negating the edge weights takes all of M, because you're going across this one array that's size m, and you're going to update, well, not update, you're going to make a new array, and then running cross-calls is O of m log n, and so your overall runtime is just O of m log n. Okay. Any questions on this problem? Oh, yeah, Ravi?
Joe, so what I was thinking for this problem, I said that we could do the opposite of finding an MST using some inverse of Kruskal or Prim's algorithm. I know it sounds too vague, but what I mean is, couldn't we do a kind of a way of like in this case, like reverse the edges, or in this case, like make the edges such that the lowest become the edges with lowest edge becomes the highest, and the edges with highest case becomes the lowest edge, and then apply some kind of Kruskal algorithm there.
You'd have to explain what you mean by that. You couldn't just say like the highest now becomes the lowest and lowest becomes highest. That's not enough detail on what you're actually doing with the edge weights. Multiplying it by -1 does exactly that. So that's exactly the right approach. I just think that's not enough detail to actually say what you're trying to say.
Yeah, of course. Now, obviously, I wouldn't do anything like that, like give vague detail on the exam. I'm just like, all I'm really doing here is giving the right, saying if my approach was correct or not. If it is correct, obviously, I expand on that. So.
Yep.
Thanks.
Yep, that's exactly what my approach is doing. Okay, Matthew.
Yes, hello. Quick question on the negation of all edge weights, because in the course runtimes, I see that operating on all edges is n plus m. So I'm just wondering why negating all edge weights is just O of m.
Yep, good question. So when you go and actually physically do something with the edges in the adjacency list, it is in fact O of n plus m, because you have to find all the edges, right? But the weight, the list of weights that's given to you is somewhat magically indexed by edges. So there is no vertices in there that doesn't have an edge. That weight array or function is purely edges. So there's exactly m entries in there. And so in order to multiply all those by -1, it is going to be O of n. It
Makes
is a
sense.
separate data structure. Yep.
Thanks.
Yep. All right. Any more questions?
Will we be treated as wrong if we actually iterate through the edges through the adjacency list and then indexing to the weight list and to apply the number change and then specify runtime of O m plus m? Is that okay?
Yep, that's fine. You can do steps that are slower than what they could be, as long as they are less than your the target runtime, which right now is dominated by Kruskal. So however you want to work with the edges and just giving the proper runtime, it's okay.
Okay, thank you.
Yep. All right. Next question is 5.20. Let's see what 5.20 is.
Sorry, Joves, sorry, before you move on, just real quickly. Kruskal returns the edges, but the edges don't have weights because the weights are their own separate list, right?
Yes.
Okay, thank you.
Yep. And when we talk about a spanning tree or like, we generally don't care about the updated weights. We generally just say, okay, well, whatever the edges or the pre array that tells us what those edges are is what we care about. You don't have to go and be like, oh, let me just revert back all the edges. Okay. All right, so this question is, give a linear time algorithm, so this is 5.20, that takes as input a tree and determines whether it has a perfect matching, which is a set of edges that touches each node exactly once. Did I do here? So this one is kind of tricky because you have to figure out what a perfect matching is. This took me quite some time to look up. Where is my? Wait, why is this not working? Mm, okay. So you're basically looking for something kind of like this. Just need, hold on, let me just double check and read this. Perfect matching, a set of edges that touches every. Okay. So it's not that you want a graph such that all the edges, all the nodes only have one edge that touches it. You're looking for a set of edges such that each node is only touched by that set of edges once. So if I had at any point, if I had like this one right here, okay, this would not be a perfect match because I would not be if I have it if I consider this edge, if I include it, this vertex now has two edges touching it. Okay. However, if I don't include that edge, this vertex now has no edge touching it. Okay. So every single vertex has to be touched, and every vertex can only be touched once by the set of edges. It's kind of similar to the coloring problem, but it's like on edges instead. If that makes any sense. You might get a better understanding when I write the solution, but you're not asking for a graph that is only touched by one edge, because that wouldn't be you wouldn't be able to have a tree, right? So you want a tree that is structured in such a way that you can collect a bunch of edges such that all vertices are only touched once by this set of edges. Hopefully that makes sense. Bing, question?
Right. Well, just a very quick difficulty check, because this one I spent a whole day to work on this. Will we see items like this level of difficulty brand new in exam, or it's very unlikely to have something like that kind of difficulty?
This question would have been too difficult for me to agree to be put on the exam.
Okay, thank you.
Yep. Equin?
Hi, so I just want to make sure. So in this diagram, at least, the black sets or the red sets, excluding that new dots you just draw, are the perfect matching. Is that correct?
Yeah. Yeah. So
Okay.
like if I didn't have this dot, then yes, I would have a perfect set because this edge, these four edges, touches every vertex at most once, and exactly once, right? So all
Okay.
vertices are accounted for, and no vertex is being touched by two edges from my set.
Okay, so the black
Yes,
edges are
the
the
black
perfect
ones.
match.
Yep.
Okay, all right,
Yep.
thank you.
Yep. I'm subtle.
Hi, so I couldn't understand why adding the blue edge makes this graph not have a perfect matching.
Okay. So if I had this additional vertex and I have this edge, right, I can't get a perfect matching set, because if I include this edge, then this vertex now has two edges touching it, two edges from my set touching it. If I don't include this edge, this vertex now has no edges touching it. So this edge right here creates a contradiction.
I see. Thank you.
Yep. And you can kind of take a look at this and consider like, oh, it's a kind of like an edge coloring problem. I want to be able to color edges such that no two adjacent edges are the same color, right? And so as I'm coloring these, I'm going through, and this right here causes a issue because I already have these two colors, and when I have these two colors, I can't color this differently. But it turns, but it's not quite the coloring problem though, because if I have this right here, if I have an additional vertex, suddenly this works. This now works. Oops. This now is okay, because this edge takes care of both of these vertices without any vertex having two edges to it. Okay, so it's not quite the coloring problem, but it's somewhat related. Okay, but this is this would be okay. But if I did not have that additional edge and vertex, this creates a problem for me. Okay. All right, let's go over the solution. Solutions kind of involved, but hopefully we can talk it out. So I'm basically going to take this graph, and I'm going to start removing vertices. I'm going to start trimming it. I'm going to trim this tree in such a way that I will see if by the time I finish trimming the tree, I can still have it. So one thing that you should notice is that all trees have leaves. There has to be, because there's no cycles, there has to be leaves to a tree. No matter how you draw a tree, there's going to be leaves. And leaves, the edge that comes off of the leaf, if there is a perfect matching set, that edge that comes off the leaf has to be part of the perfect matching set, because this is the only edge that touches this vertex. So this edge must be included in the set so that all vertices are touched. Now, if this edge isn't included for any reason, then this vertex cannot be touched because it's a leaf, and therefore it's attached with a bridge, and that bridge is needed in my perfect set, right? So what I'm going to do is I'm going to get the degrees over my vertices in the tree. And I'm going to make a list of all the 1 degree vertices. These are my leaves, okay? For all leaves in T, my tree, there exists one edge, right? We're going to add U and V to a touch list, okay? So we're going to say, okay, well, we're going to take this edge, right? We're going to say this one is touched, and this one is touched, okay? We have touched those vertices in my perfect matching, okay? And then we're going to add that. We're going to remove that edge, okay? And we're also going to say, okay, this edge is now. Wait, is the question asking if there's a perfect set? Okay, all it's asking is if there's a perfect match or not. It's not asking me to keep track of the edges, which is why I don't. Okay, so now I'm going to say, okay, I have to include this edge. I have to touch this vertex, and I have to touch this vertex because I'm including this edge. Now I can delete this. I no longer need that edge. Okay. I will also delete all edges touching this vertex. So like if there's a whole bunch of edges here, none of those edges can be part of my perfect match, right? Because then this vertex can be touched. So I'm going to remove that. Okay. And then the other thing is I was going to do this for all my my single degree. So that's 1 degree. That's 1 degree. These originally were not. Okay. So now once I attach, I'm going to say, okay, this one's touched, and this one's touched. Okay. Wait, hold on. I have to do these in order. Sorry. Okay. So I say that one's touch. I say this one's touch, and I'm going to remove this one. Okay. So the next thing I'm going to do, add U to a touch list and remove UV, and then remove all the edges that touch it. Okay. Update the degree of vertices as we do, and update the list of 1 degrees. Repeat this until either all vertices are touched or a vertex is disconnected. Okay. Okay, so what happens here, if I get here, okay, so it's saying, okay, I touch this, and therefore I remove this. My next one is going to say, oh, wait, okay, hold on. Let me go back. All right. I'm going to remove this. Okay, so that's good. Next, I'm going to work on, let's say, this one. Well, this is touched. This is touched. This is touched. This is touched, right? So I grab my 1 degree vertices, I touch the 2 endpoints, and then I go and I start deleting. I delete this edge because that's touching that. I delete this edge that's touching that. Delete this edge because it's touching that, and I delete this edge touch that. And look, this vertex is now untouched. I have considered all my perfect match sets. This vertex is now disconnected completely from my touched set. And so I cannot find an edge that will handle this vertex, and therefore this tree that I have drawn for you is not a perfect match. Okay. Now what happens if I had done this with an actual perfect match? The other thing I did was what? This. Oops. All right. Now, visually, we can see that this has a perfect match. Let's make sure our algorithm works, okay? So we get all the, all the 1 degree vertices. We grab them. We said everything on the other side of the edge, we grab those as being touched. Okay, and then the next part is to start deleting any edge that's attached. Okay, good. Now the next part is, okay, now I look at the remaining 1 degree vertices and I mark them as touched. Cool, cool. And then I say, okay, the other side of this edge is touched. Cool. And then I delete all the edges that touch that are attached. And there we have touched, or we have grabbed every single of our vertices, and therefore we have a perfect matching. Okay, so that's what our algorithm does. If all nodes are touched, which it is, we return true. If a node gets disconnected, then we return false. Okay, so those are 2 runs of the algorithm. Okay, so the correctness is that all leaf nodes must have the only edge that connects to it included in the perfect matching. Once that edge is included, then both endpoints are touched and no edge that connects to them may be included in the perfect matching. So by touching vertices and removing incident edges, we keep adding valid edges to our perfect matching. We know a tree must have leaf nodes because they're underneath cycles. And because removing a leaf node leaves us a tree, that's just a true statement for trees. We can keep doing this until we have found a perfect matching. If at any point a vertex is disconnected, then it means the edge it uses to attach to the tree is invalid, and we can't touch the disconnected vertex anymore, and therefore it's false. Okay, so getting the degrees of all vertices is all of n plus m. We just basically go through every vertex. We check for edges, check to see what their incoming edges. In fact, I think this is actually yeah, it's all of n plus m because I have to know how many edges are attached to each vertex. Pruning the tree 1 vertex at a time, along with edges, is all of n plus m total, and therefore our total runtime is n plus m. And the reason why you need to have all the degrees of your trees is because as you trim your tree, you want to also keep track of what the degree is of the other vertices. So I know that if I remove this edge, then this drops this this degree by 1, and therefore my next set of 1 degree vertices, I don't have to scan my entire tree again. I can just say, oh, okay, well, I know which ones were 1s. Okay. Questions about this? Mahmoud?
Hi, Jonas. So I saw here that you did, for example, update the degree of vertices as we do this, update our list of 1 degree vertices. Is it assumed that we can just say find the vertices with degree 1, or do we have to explain how we find it? Just in general, because this is something that I was trying to use in another question, and I was struggling to figure out how to solve it or say it if need be.
I would put in the step on how you get the degrees of trees just to be safe.
Okay.
Yeah, I think that probably is best.
That's fair. Okay, thank you.
Yeah, let me add that in so that there's no confusion. Okay, get the degrees of all vertices in the tree by checking the length. Right. Get the degrees of all vertices in the tree by checking the length of the edge list for each vertex. Right. I think that's good enough. All right. Any other questions? All right, cool. I do like that question quite a bit because it made me really think about like how a tree is constructed in its relationship. I do think it's a little bit too difficult for an exam question. All right. All right. I like this question a lot too. Okay. So you're given a graph G with positive edge weights and a minimum spanning tree T with respect to these weights. You may assume G and T are given as adjacency lists. Now, suppose the weight of a particular edge E is modified from WE to a new value W cap E. You wish to quickly update the minimum spanning tree T to reflect this change without recomputing the entire tree from scratch. There are 4 cases. In each case, give a linear time algorithm for updating the tree. Now, the main thing here is that you don't want to rerun your MST algorithm, and this is going to be a thing that you might run into on the exam or in the homework problem, where it's like you have an MST already and now you need to update it. If that's the case, it is almost certainly not optimal to just rerun Chris-Gauss. First of all, that would show no mastery of the topic at all, right? Saying, oh, I would just run Chris-Gauss, return it, solution. 2, it is highly unlikely that that is going to be optimal. So if you do that on the exam and then you get angry that you lost a lot of points and saying, oh, but it's a correct solution. Yeah, it is, but it's basically a brute force solution that's like 1 sentence long. And if you're writing 1 sentence solutions in this class, you're probably doing the wrong thing. Okay. All right. So part A is saying if my E, the E that I am changing is not part of the original MST, and then its weight increases, what do I do? Okay. And the answer to A is you do nothing. Exactly. If the weight of that edge was already too big to be part of MST, or it was not, if it could have been in some MST, let's say that it's equal to one of the edges that we chose. Remember how I drew up, the Chris-Gauss run in office hour 1, and I said, okay, there's a 3 and a 3, and you can pick either one. If one of those goes up, if one of those 3s goes up, it is now not part of the MST. It could have been part of the MST, but it's now not part of the MST, so you don't do anything. If it wasn't part of the MST to begin with, because it was too big, making it bigger doesn't change anything. So part A is you do nothing. Okay. Okay. All right. Part B says it is not part of the original MST. Okay. But now it's smaller. Okay. And this is important because this edge could be part of our MST, or it might not be part of our MST. Okay. So the question is, how do we figure this out? Okay. What you want to do is you want to run, if you want to get the path information from U to V, right? So we have a graph that is some like, some U. Oh my gosh, why are you so big? U, some V. We don't have an edge here, right? We know that this edge is not part of our MST, but we have some series of edges along here. It doesn't really matter what, that connects U to V because all vertices are connected in an MST. Okay. So what I want to know is that if I was to add this edge here, I will have created a cycle, right? And if I created this cycle, then the heaviest edge of this cycle cannot be part of the MST, all right? But I don't want to add this edge and then look for the cycle because that's not really, that's not super easy. So remember how I asked you how yesterday there was a question like, how do you find out if an edge is part of a cycle? Well, you remove the edge and you run BFS from U and get the distance to V, right? So similarly, what I want to do is I want to run BFS from here, right? Which will then give me a path to V. Okay, so it'll discover this path to V. Okay, now the path from U to V is unique, right? We know this because it's MST. So that means that from here, from V, from my path to V, if I run BFS from U, I'll have a previous array that goes from V all the way back to U. And using that, I can check to see what the weight of all these edges are. So I can check what the edge of this one is, and what this one is, what this one is, this one is, this one is, this one. If any of these edges are greater than the edge that has been updated, right? So if this edge update is now lighter than any of these edges, that means I can add that to my MST. And in doing so, I can now delete the heaviest edge I discovered. So now this is a proper MST with the new updated edge. And I know that this will create a cycle by adding it, but I have also removed an edge that I know will break the cycle. And because no other cycles exist, I know this won't create a cycle. And so I know that this is my new MST. Okay. So that is the solution to this one. I will post up the paste right up. All right. So let E be whatever our represent UV. We run BFS on T from U, find the heaviest edge along the path from U to V using the brief array and the weight array. And then if the W of the heaviest edge is greater than our new edge weight, then remove it and add E to the MST. BFS takes O of n plus m time, checking to see the heaviest edge in a previous array is O of n. And that's it. Jackson?
Hey, Jovis. So more general question. When it comes to justification for some of these problems, I mean, that we've discussed many different graph properties. Which is there like I don't know, guidelines or, things that we have or haven't proven that we're allowed to use in our justification? That make any sense?
All the properties that you've learned about a MST, like for this particular problem, you can use as truth in your proof. or anything that we've are given expressly as properties of graphs, you can use as part of your proof. But you can't take like, oh, I have one algorithm here that I worked on that shows one thing, and then transpose that onto the problem you're working on as if that to do it. So like all these properties that I'm talking about are actual, truth or theorems or laws that's already been proven.
Got it. Makes sense. Thank you.
Eduardo?
Yeah, thank you, Joves. So one general question and one question regarding this part B. If we're ever interested in knowing the weights, any algorithm, Kruskal's or Prism would give us that output? Because I thought it was for Kruskal's we only get edges, and for Prisms we get prep. So I'm not sure which one is preferred for knowing the weight.
Of your
MS,
of the
yeah,
MST?
Yeah, of the MST.
I would use Kruskal's. I think Kruskal's is just easiest. The MST makes the most sense to me as a series of edges. I think Prims gives you back the pre array, which is fine. I seldom find a reason that I need it. I almost always just want to know which edges are part of the MST.
Got it. And then regarding the solution for this one, how is BFS giving us the heaviest edge? I know that the outputs are distance and previous.
So the BFS tells me, the BFS specifically tells me the path that's being taken from U to B. And then I use that, and as I go back through the prev array, I know what edges create that path, and I'm using that edge to look it up in my weight. So find the heaviest edge along the path from U to B using the prev array and the weight function.
Yeah. Okay. So from running our original MST algorithm, right?
Yep.
Yeah. Because BFS wouldn't give us that. The weights, I mean.
Right. Yeah. And before any student asks, I could have done DFS and it would have been fine. All right. Manjunatha?
Joes, can this be solved using the cut property instead of cycle property? That is, the edge was existing in the graph, and then you go and look at the UV, all the edges currently connected, and then look at all the weights, then disconnect the one that is heavier than the newly updated edge.
I mean, yeah, that's exactly what I did. I looked at all the edges and I decided which one was the heaviest and I disconnected it.
No,
but how do you find it?
Yeah, that you went through all the path from connecting U to V, right? Instead of that, look at the U, all the edges outgoing from the U, similarly outgoing from the V, and then look at all the weights. If the updated edge's weight is lesser than any of these current weights going out of U and V, can we disconnect the heavier one and then use the updated edge E?
No. I mean, what if my situation is that I have this really heavy edge to G? Like why would disconnecting this? Yeah, what would disconnecting do? Like I actually have to find this path right here, so I know what part of this path I can rip out. Because ripping out this edge doesn't do any good. I can't just take this out and add UV. I would get a disconnected graph.
Thank you. Yeah.
All right, Nicole.
Yes, thank you. I had one question for like the exam, and my apologies if you went over this yesterday. But when we say like, we're using the prev list to find a path, using BFF or DFS or any other ones, do we have to spell out how we're doing that, or is it okay enough?
You can just say use the prev array to find the path. That's fine. That's a known process.
Perfect. Thank you.
Answer one more question and then I have to move on. Lemfen?
Yes. Do you mind just listing the time complexity by doing this whole step? Like you find the largest, the weight larger than the new weight, and then
It's O of n plus m to do the BFS, and then O of n to find the heaviest edge. Because you are going to traverse the entire previous array, and the previous array can only be of size n. Like if t is 2 at the ends of each other, it would take O of n because it's how many vertices there are. It's also how many. You can't say O of m because the number of edges in your graph is not the same as the number of edges in your tree. So you want to say O of n, and then it's just a O of 1 lookup for each one. So it's O of n plus m and O of n. That's it. The overall runtime is going to be O of n plus m.
Okay, thank you.
Yep. All right. Part C is my my edge is already part of my MST, and it's shrunk. So it's gotten smaller. It was already in my MST and it's gone smaller. So what do I need to do next? Yep. And once again, I do nothing because if it's already part of my MST, all it did was lower my overall MST. It doesn't change the fact that it's part of my own MST, right? We just don't have to do anything. Exactly. Good job. All right. So the next one is another tricky one. My edge is already part of my MST, and now I want to it gets bigger. So what do I do now? So now what I do is I want to perform a single operation of constructing MST. Okay, so I don't want to reconstruct it, but figuring out the lightest edge across a cut is a O of n plus m step. It is linear time. I don't need to sort it because I know I need one of those edges, and so then I just have to check every single edge that crosses that cut, and that's all I have to do, right? So I just remove E from T to get two components. I find the lightest edge across the newly created cut and add it to T to update the MST, right? So this is an application of the cut property and takes all of M to find the lightest edge across the cut. Okay. There's other steps to it where you have to if you were to do this as an actual algorithm, you have to actually discover what the cut is. You can run either DFS or BFS for this. You can run BFS from U and everything from U, and then everything you can reach is one cut. Everything you can't reach is the other side of the cut. And then, or you can do DFS, and you'll get two CC nums, and those are your two halves or two parts of your disconnected tree, and then you just find some edge that crosses that cut. Okay, not too much detail because I don't think this is asking for like a full write up of an algorithm, but you would have to figure out where the cut is, and you could use either DFS or BFS for that. Jafar?
Yeah, sorry for taking you back, but my question was to ask you how we need to identify this in details. So if we want to explain how to get the cut first, and then we need to explain. So how to write it in the exam? If we are saying we need to find the cut, and then inside the cut we need to check all edges coming out of the cut. Okay, those concepts I understand them correctly, but how to write them? So what should we write in the cut? So how we are finding the cut? It's not trivial to say we find the cut.
Yeah, so I would say,
yeah.
like I said, you can say run DFS from U, run DFS, and then you have your two connected components, right? And then whatever the two connected components are what create your cut, and then just go through every edge, and if the edge has one vertex in one part of the cut and a vertex in the other part of the cut, then that is an edge across the cut, and track all those edges and find the lightest edge, and whichever is the lightest edge is your new edge. Now, if those that lightest edge could possibly be the edge that was recently updated, and that's fine. But you can just say find the lightest edge across the cuts. Once you have identified the cuts, go through all edges where one vertex is on one side and one vertex is the other side.
Okay, I understand. Okay, I understood the first part. We say that the DFS will help us find the components, but then we need to find all the edges between the two components.
Yes.
What is that in words? So which algorithm we are using here to find the edges between those two components?
I mean, you know the connected components of all your endpoints, right? So on any given edge, I have two endpoints. I look up the connected component of one edge, one vertex, I look up the connected component of the other vertex, and they're in the two different connected components, then it is a edge across the cut.
Okay. Okay, understood. Yep. Okay, thank you.
Yep, no problem. Any other questions about this particular problem? Cool. Oh, yep, Mahmoud.
Yeah, sorry, Joves. I know you've already explained it twice. I can't comprehend how to find that connecting edge. Is there any way you can maybe like draw it out just so I can visualize it a bit more? I'm sorry.
That's fine. So let's say I have
this would be very helpful.
Some MST, right? And let's say I have deleted. Well, I'm going to delete the edge that got updated because I don't no longer know if this is the message, right? And so I'm going to run DFS. And DFS is going to say, okay, all these vertices, let's use a different color. All these vertices has CC equals 1, right? All these vertices has CC equals 2, okay? And so I go through all my edges. I have an edge list, right? So for any given edge, if my edge is, U, B, right? I check to see if I check the CC num of U and I check the CC num of V. And if it's the same, they're still in the same connected components. That's not an edge across the cut. If this is in CC number 1 and this is in CC number 2, then that is a candidate edge. And what candidate edges will look like is like, anything that's going from this connected component to this connected component. So like if I had an edge right there, an edge right there, and an edge right there, all these blue edges are edges I want to now consider as possible replacements for the edge I removed. Okay, and if the CC num of this vertex and the CC num of this vertex are different, then I know it's a edge across the cut. If the CC num of this vertex and the CC num of this vertex are the same, then I know they are not an edge across the cut because I want them to be of the two separate CC nums. And so at that point, every edge that has different CC nums for its vertices is a candidate. And then I just look up its edge weight and then just track the lightest one, and whichever is the lightest one is the one I end up using. So, I check these and I go, okay, I check this one, it's really high. I check this one, this is really high. I check this one, this is really high. And then I go, oh, okay, well, this one was the smallest of all the edges that I knew crossed the cut, and therefore this is the edge I'm going to keep. And now this is my MST.
So, I understood. You ran the DFS on the tree, and then you use that CC num to find the edges in the graph. And that's how we find the shortest edge, the minimum between them.
Yes.
Okay, thank you so much.
Yep. Iquan?
And Joves, so the edges that just update the weight, that's one edge should also be included when you...
Yeah. So you just check all your edges. Yeah. You check all your edges. Yeah. Because even like if that edge that you updated was so small to begin with that you added it and it was still the lightest edge, you want it to be considered. And nothing about what I wrote would suggest that that is no longer considered. Okay. All right.
Okay, thank you.
Move on to the next question. Yep. So that was 5.22. We are going to look at 5.23. So this question is saying that sometimes we want a light spanning tree. So careful, not the lightest spanning tree, but a light spanning tree with certain special properties. Here's an example. So you have a undirected graph, edge weights, and a subset of vertices U, which is subset V. The lightest spanning tree in which the nodes of U are leaves. There might be other leaves in this tree, but we want the U to be leaves. And you want to give an algorithm that runs in this runtime. When you remove nodes from U from the optimal solution, what is left? Okay. So that is the presentation question. Another somewhat similar question, not exactly similar to this, but another question is, I think one of your homeworks. I think it's homework 8, where we wanted you to construct a similar lightest spanning tree, light spanning tree, not necessarily the minimal spanning tree, but a light spanning tree given some conditions. So that's a very common spanning tree type problem. Okay. So I have 2 solutions for this. I think I want to just present the easier one, and that's it. I'm going to present the second solution. I think the second solution is simpler. All right, so you're basically going to start by creating a partial MST, and then you're just going to go and add each vertex back to the partial MST. And because you add it at the end and the partial MST is already built, then adding them back as to the MST at the end makes them leaves. Now, one thing you should, it's not given to you, but we're going to assume is that a solution such as this does exist. When we give you a problem like this and we don't say, tell us if a solution doesn't exist, you can assume that the solution will exist. Okay, so we remove U from our list of vertices, V, and then we're going to call this model graph G prime. Then we're going to run Kruskal's on this, and we're just going to get a partial MST. Okay. Now we can also check to see if this partial MST is already an MST, because if there's any it would not work. So this partial MST must be an actual MST of the vertices that remain. So for each vertex in U, find the lattice edge that attaches it to the partial MST, making sure never to connect to a vertex that was in U. So if you add U back to this partial MST, you can't then also attach another vertex to it, because then the vertex you just connected will no longer be a leaf. Okay, and then we return this as the full MST. So we seek to the correctness is that we seek to get an MST such that all vertices in U are leaves. By removing all the vertices in U and then running Kruskal's, we get a partial MST such that we add vertices U back to it. They will always be leaves. We take care not to attach to another vertex in U, and you have to explain this part because you made a step, you called it out. So why did you do this additional check? Because if you did that, then the vertex will no longer be a leaf, right? So this works because the cut property allows us to take the lightest edge between U and the partial MST, and that works. Okay, so removing all the vertices takes O of n plus m. All the vertices we want to as leaves takes O of n plus m. Running Kruskal's on that takes O of n log n, and then adding U back to the partial MST over the lattice edge is O of n. We consider all the edges that goes from our set of vertices that is not part of the MST, and we just check all the edges that are in one section or the other, and then we add it back. And that's it. So it should be O of n log n. Questions? Lennon?
Hey, Joves. Yeah, so this is different from the problem that they had listed on the
Oh, is it?
Yeah, it looked like whatever. I don't know if you're using the same source for the book that I'm using. I found a website for it, but it seemed like the numbers were out of order, or the problem numbers are out of order. I think the 5.23 they listed was the one that you just did, and then 5.22 was a totally different problem.
Let me see. 5.22.
They said it starts with, in this problem, we will develop a new algorithm.
Okay, let me see. Okay, so 5.22 is 5.21, which is what happened in your command graph. Okay, so I gave you one. Okay, so 5.21. Your find minimum string trees is based on. Oh, I hate this problem. I disagree with this problem being given, but I'll tell you the solution to this. Okay. God, this is such an irritating problem to me. Is this
Yeah,
a
we could
problem
we could totally skip over it. I just didn't know. I didn't know if we
all
were
right.
ever gonna go over it.
In this problem, we will develop a new algorithm for finding minimum spinning trees. It is based upon the following property. Pick any cycle in the graph and let E be the heaviest edge in that cycle. Then there is a minimum spinning tree that does not contain E. Okay, so that is the cycle property. Okay. So we want to prove this property carefully. What did I write? Okay, that's fine. I'll paste my entire solution and then we will talk about it. And then we will pretend this is what I did to begin with. Okay. So here we are writing a proof for a cycle property. And I might have actually looked this up because I know it's a proven property, but I might have rewritten it to in a way so that makes sense to me. So okay, suppose we have an MST that includes E, right? So this is edge. If we remove E, we now have two components that are disconnected. Okay, that's what a MST happens with the MST. We seek to reconnect them with some other edge E prime, such that the two components are connected as an MST again. For the original MST, there exists some E prime that was left out of the cycle that E belongs to, right? So if that thing was part of a cycle, then E belongs to a cycle, and we can use a different E to do it. Okay. So we also know that the cost of E prime is less than or equal to the cost of E. Okay, since E is the heaviest edge. Okay, so this is saying that suppose that E is the heaviest edge, then and it was part of an MST. When we take it out, there must have been another edge among this cycle that was less than our unique heaviest edge, right? So then replacing E with E prime must therefore give an MST where the new cost is less than equal to the original MST. So some MST must exist that does not include E, but includes E prime instead, right? So this is saying, again, by proof by contradiction, that if our heaviest edge was part of some MST, I can remove that heaviest edge and find another edge within that cycle to put back into this MST. But if I put back another edge that was lighter than the heaviest edge that I took out, that now creates this MST because I can remove an edge and add another edge that's part of the cycle. I have effectively made my MST smaller. And if I make my MST smaller, then my original claim that this was an MST that includes the heaviest edge could not have been an could not be an MST to begin with. So therefore, the heaviest unique edge of a cycle cannot be part of any MST because it can always be improved upon simply by being part of a cycle that has lighter edges. Okay, so that is that. Okay, part B is saying once we've proved that property, here is the new MST algorithm. The input is some undirected graph G in the adjacency format. And then what we're going to do is we're going to sort the edges according to their weights. For each edge in decreasing order of W. So we're going from heaviest to lightest. If E is part of a cycle G, then we are going to remove it. And then we're going to keep trying. So as long as we have cycles, as long as our edges are part of cycle, as we go from heaviest to lightest, we're going to remove it. Okay. Prove that this algorithm is correct. Okay, so by proving, we're saying we know that Kruskal's algorithm to be true. If Kruskal's algorithm adds minimal edges until a cycle could be created, then the reverse of this process is also true. We remove maximum feedback edges. Feedback edges are feedback edge is the term you use when a edge creates a cycle, and if you remove it, it removes the cycle. So the maximum feedback edge until all cycles are removed. Removing the edge from a cycle leaves all vertices still connected and satisfy the MST connectivity. So as long as we're looking at cycles, we can always remove edges. As long as we remove the heaviest edges, we are leaving the lighter edges intact. And as long as we keep removing the heaviest edges until there's no cycles, then the lighter edges of those cycles, which stops creating a cycle, will remain. So it's the opposite of Kruskal's. And if Kruskal's going from lightest to heaviest works by adding edges until you have a cycle. Going in the reverse also works. So that's part B. Part C says, on each iteration, the algorithm must check whether there is a cycle containing a specific edge E. Give a linear time algorithm for this task and justify its correctness. So we can take an edge that we are considering, is this part of a cycle? We can remove that edge from G and then run BFS. If V is reachable from U, right? So we've seen this before. Take an edge, remove it. If U can still reach V, then UV was part of the cycle. If not, then UV was not part of the cycle, right? So if it's still reachable, then it is a cycle. Okay. So now doing this is the BFS is all of n plus n. So what is the overall runtime of this algorithm in terms of E? Explain the answer. So by sorting the edges, it's all of n log n. Okay. For each edge, run BFS. So that's all of m times all of n. We say it's all of n because it is a MST problem. If it's an MST problem, then the graph is connected. If the graph is connected, m is greater than or equal to n minus 1, and therefore, yeah, so m dominates, so we can drop the n from the BFS. So it's m times m, which is O of m squared, right? And that dominates your sorting of edges, which is used to be the part that makes Kruskal's and Prim's its runtime. But now we have dominated that part of the runtime, and we end up with O of m squared, which is equivalent to O of magnitude of E squared. And this is pretty bad. This is a bad algorithm. Don't do this. Okay. This is why we don't use the cycle property to create a MST. We use the cut property because it's more efficient using Prims and Kruskal's. Okay. Questions? 10, 12?
Hey, Joves. Thank you for the office hour. I think my question is around the previous questions. 523. So
I don't even know what these numbers are anymore. Go ahead.
yeah, so when I worked on this question, I kind of feel like it is a MST questions, but I was keep thinking, okay, if I remove V, like all the nodes from V, and then run Crisco on the leftover graph, is any like situation or edge cases like they're not connected, so that will cause an issues.
So I didn't bother writing this because, like I said, if we present to you a problem and we don't say, tell us if it's impossible, you can assume that it's possible. And so I took that assumption here. But a really easy check for this would be if you take away the U vertices and you run Kruskal's and you don't get back a MST, or Kruskal says we can't build an MST, then the entire thing fails. Because in order for the partial MST to still be part of the MST under these conditions, you'd have to connect them using a U vertex. And if you connect them using a U vertex, then U vertex is no longer a leaf, and so the entire problem just doesn't work. So you could put that detail in there if you wanted to, but I just left it out. I just assumed there would be a correct answer.
Gotcha. Thank you.
Yep. Mahmoud?
Yeah, I was getting confused with the ordering of the book because to me this was a different problem and I'm getting lost in the numbering. So sorry.
Okay. Yeah. No, it's no problem. This confused me too. I'm gonna ask for this problem to be taken away from, because going by what was listed, the implication would be I do this problem, which I think is generally not a great problem, and I skip this problem, which I generally think is a very good problem. So I would rather show the answer to this problem and not this problem because I don't like this problem. Or we could just have both. Why not both, right? So maybe I'll just get Tim, who is the person who maintains this list, just to add both problems, and then I can solve one problem I don't like, but also solve a problem I do like. I think that's fair. right, no more questions? All right. So that was the last MST problem. I am going to take about a 2 to 3 minute break, or give you a 2 to 3 minute break, and then answer 1, 2, 3, 4, 5 max flow problems. Hopefully I can do those in about half an hour, and then we'll be done around right before 9:30, and then I can have dinner. I'll be back in about a couple minutes.
Thanks, Jovis.
Max flow problems. Everybody loves max flow problems. Let's see. Jafar, you have your hand up?
Yep. So I want to ask a small question about the cycle property. If you have time now before we start the yeah. So we said that the minimum edge of a cycle may
The
be
maximum
not
edge. The maximum edge of a cycle. The maximum unique edge of a cycle, specific. It has to be unique.
okay. So the maximum unique edge of a cycle cannot be inside the MST. But the
Yep.
minimum edge of a cycle may or may not be in the MST.
MST. Correct.
May or may not, because it may be the maximum of another cycle.
Right.
Yeah, but the minimum edge of the tree in general is definitely inside the MST.
The unique minimum edge of a graph is always in every MST. So I went over all of these on, I want to say, the second week. So if you haven't seen the second office hour, so if you haven't seen those office hours, I go over a lot of these.
No, I was there. I was there. Yes.
Okay.
But maybe a lot of information, so I'm a little bit struggling because you said in the quiz we don't have we have a question that said edge of minimum weight is in the minimum spanning tree. This is false, but I think this is true because it is false if it was inside in a specific cycle.
So ask your question again.
So you said while you were talking before today, you said that there was a question in the quiz that the edge of minimum weight is in the spanning tree. This is false.
The unique minimum edge of the entire graph is in every single MST if it has an MST.
Okay.
The unique minimum edge of a cycle may or may not be in an MST.
Yeah, because that question was not on the quiz, or maybe.
I don't know what's on the quiz. I don't
Okay.
know what's on the quiz. Yeah.
Okay, great. Thank you.
Yep.
Okay, thank you very much.
You could?
Hi, Joves. I just have two quick questions on MaxFlow since we started. Number one is building a residual network considered a black box, or every time we use, say, I want to build a residual network, we need to instruct in detail how to build a residual network?
It's not so much a black box, it's just a known step. So you can just say build the residual network. It's fine.
Okay,
it's similar to saying reverse the graph. Like there's not a black box per se, but like we know what that process means. Just like identifying the once you've identified a cat, saying like the find the lightest edge across that cut, find the heaviest edge across the cut. Like we know what that means as long as you tell us how you identify the cut.
Okay, cool. Thank you. The second question is, when we were given a MaxFlow min cut problem, do we assume that the flow are integers, or we cannot assume that by default unless otherwise explicitly said the flow is not an integer, because that depends on whether we can use FF.
I would not assume it. I would just say that like if we tell you the weights, if we tell you the capacity of a flow network and we don't specify that it's integers, then don't assume it is integers.
Okay, thank you.
Yep. All right. We are now moving on to 7.18. AB. Right. So there are variations of flow problems. Here are 4 of them, but we only care about the first 2. There are many sources and many sinks, and we wish to maximize the total flow from all sources and all sinks. So what we're doing with this first one is basically saying, okay, well, we have a whole bunch of sources. And the way to Sorry, I'm having trouble. The idea is that we want to turn these into normal max flow problems so that they can be solved. So if I have a max flow problem with an S and then some A, some B, and I guess it doesn't really matter what these letters are. Right. So you normally only have one S and one T, but in this version, I might have multiple S's and multiple T's. So if that's S1, this might be S2, and that goes like that, and then this might be T2. That could potentially go to another one. Okay. Or something like this. Okay, so you have this like super network of sources and sinks, and now we want to maximize the overall flow from all the sources to all the sinks. This is going to look a little difficult. If I was to rewrite this, I'd probably write it a little bit more narratively. But at the time I was writing this, I just thought writing it all out in symbols and math notation was easiest for me to. We're going to let S be all source vertices. So we create a subset of we just want to talk about it, and then we let T be all sink vertices, and so we create S prime as a super source, and we create T prime as a super sink. Okay, and by doing this, we now create G prime, which is equal to V prime E prime, such that for every vertex, we add our super source and super sink to it. Okay, so what that would look like is saying, okay, I'm going to create the super source, okay, and create such that V K E is from S. Where am I? Something is wrong with my my tablet. Okay. So I'm going to connect my super source to all sources, and then I'm going to connect all my sinks to my super sink. Okay. So here we're going to go like this, like that. That's a 1. That's a prime. I apologize for my ugly handwriting. And then we are going to create these capacities, but all the capacities are the same, but this capacity right here is going to be infinite, and then this capacity right here is going to be infinite. Okay. And then we're just going to run Edmund carps with this new super source and super sink. And then once we get back our flow using the super source, super sink, we are going to return our flow. But when you return the flow, and this is something that you have to be very careful of going forward, is that when you modify your input and your output is dependent on your input, you can't just return that output exactly as is as the solution to your problem, because that output is going to have additional information that doesn't make any sense to the original input. So whenever you modify your input and you get a different output, and that output, your solution depends on the output, you have to clean it up. So what we're going to do is we're going to remove all the flow that has to do with the super source to all the sources and the super sink to all the sinks, right? So we just remove all the additional flows that we created by creating the super source and super sink, and then our flow is just whatever remains. And so the correctness is that because source can provide unlimited flow and sinks can receive unlimited flow, we need to represent this flow network. And so to do so, we add a S prime, T prime with unlimited flow, and then running the max flow algorithm, all edges into sources and edges out of sinks are not bottlenecks. So once we have our modified flow, max flow, remove the edges. The other thing I think you can potentially do is you can take your sources and your sinks and you can combine them into a single super source and a single super sink. And so any edge that you have coming from S1 to SA, that flow, right, remains the same for your super source. But you see how you have a flow from S1 to B and S2 to B. So in your super source, if you were to do this combination of like all your sources or your sinks, it would be the sum of this flow. So S1 and S2, the flow, because the flow coming out of S1 and S2 is not constrained in any way, then the flow from the super source to B would be constrained by both of these edges together, because you're not so, and once you do that and you get all the flows, you now have to split up the flows again, right? So you have to, whatever flow you send through this this combined pipeline, what comes out of B will properly be constrained already. So then your S1 and S2, you can just say, okay, well, if this is 5 and this is 7, and for whatever reason my combined flow is say 11, I can just assign 4 here and assign 7 here, or I can assign 5 here and 6 here, and that'll be fine. You can just assign however you want, because the flow coming out of these doesn't matter too much. So you could do it that way too. I prefer this way. I'm not going to show you the other solution, but if you wanted to try to write it up that way, you can too. Okay, and so then the runtime for all this is that creating this new graph takes O of n plus m time, because you are going to add at most n additional I guess it would be n. I think this should be n. Well, I think for me, when I go create this graph, I'm saying I'm recreating the graph, but this could be just O n. Do I want this to be O n? Yeah, let's make this O of n. I like this as O of n better. I don't like it O n plus n. So it's going to be O of n because that's how many vertices that could be possible vertices in your graph that could be sources and sinks, and you're adding an additional edge for each of your sources and sinks. So it should be just O of n, and then creating this new C dash is O of n plus n. Although actually, no, you know what? O of n plus m is fine, because you're creating a new graph, so you're taking the other graph and you're creating a brand new graph. I think it's how you want to word it. You can either say I'm going to add to G, if you want, and if you add to G, it's O of n. But I say I create a new graph, so my creation of this graph is a complete copy of the previous graph plus all the new sources and all the things. So it's going to be O of n plus m, and then creating C prime, which is all of my other capacities plus additional new edges. So my new edges is at most n, and my old edges are at most m. So it's going to be O of n plus m to get new capacities, running admix carb over n squared, removing all the flows that are from the super source and super sink is O of n, and so it is Hamasato?
Yeah, I'm curious about the second method you said. For that one, if we were to use it, how would we return the new flow? Because we kind of combined, how we would undo the combining.
On the second method I said.
Yeah.
I said it. So like once you have the flow to your, your combined, like your super source to your to B, you combined two flows of B. You can just divide them however you want, as long as they fit under the constraint. Because whatever that super edge or super capacity is going to be is capacities, and then you can just assign them however you want.
Oh,
as long as you maintain the separate capacities, right?
Okay, thank you.
Yep. Stuart, thank you for updating. Mahmoud, thank you for updating. So these should be F primes and F primes here. Okay. Okay. Any other questions? Right, cool. So part B. So, what did I do? I think I meant to grab right here. Right. Part B says each vertex has a capacity on the maximum flow that can enter it. So what that is saying is that we take my ugly graph again, and these right here, these nodes also have a capacity. So this might be 7, this might be 8, this capacity might be 6, right? So even though you could take in 7, you could exit 8, what you're going to do is you're going to constrain the incoming flow to 6 because these vertices also have a capacity. So the way we want to work with that is that capacity is really handled by edges. So if we wanted to add a capacity, we can take a single vertex that's incoming flow and outgoing flow, and we can split this vertex in half. So we have incoming flow to, and then we go, and then we reattach these edges, and we say, okay, whatever this was, let's say 6, we now apply a 6 capacity to this edge, and that means that this connection right here, which is closed off, will now be constrained by this 6 capacity. Right? So let's see what that solution looks like. I think at some point I should really rewrite these solutions to be a little bit more narrative. I don't like the way they look. I'll do that after this. So let CUV be the capacity of UV, and let CV be the capacity of vertex. So we're going to create this new graph such that our V prime is the source. Someone's not muted. Our source plus a new series of vertices that is V in for all V and V out for all V, except for the source. You cannot split the source because the source is not going to have a capacity constraint on it, because the source, has unlimited flow coming in, so the source won't have a capacity on it. And then similarly on all the edges, you're going to take all the previous edges, but you're going to take from V in to V out for all vertices, and then U out to V in for all vertices. So that basically says that I am going to take everything that's coming into this vertex. I'm going to now put it into A in, and then I'm going to take everything that was coming out of this vertex. I'm going to put it into my A out. Okay, so that's the construction of this new graph. And then I'm going to update the capacity. So my capacity for everything is going to, on the U out V in is still going to be the same. But for wherever I had a capacity for the vertex, I am going to apply that capacity to the new edges I made between V in and V out. Then once I have all that, run every card, get back my flow, and then I am going to update that flow with all the information that I get. So I'm going to remove all the flow of, and this is also something I need to update. Let me see. 1 second. F prime is the plus of FUV. This is why you should write this in narrative form because it looks ugly otherwise. Okay. So I am going to set my flow UV to U out V in for my F prime, and then I'm going to minus all the weird additional flows that I had to create in order to set up my graph. And so once I have that, that's my return flow. And so my correctness is that we update G to add additional vertices and edges, which represent the capacity at each vertex. In order for the vertex capacity my runtime is O of n plus m to create the new graph again. Updating the capacity is O of n plus m. Yeah. And then image carp is O of n m squared. And then removing all the extra stuff is O of n plus m. And then so my final runtime is O of n m squared. Okay. Jafar?
Yep. So for me, I will think about instead of adding a vertex and an edge, maybe adjusting the edge capacity. To do that, I reverse the graph, I adjusted the capacities, I reversed back the graph, and I worked with Edmond Carp another time.
So if
And
you
this
had
is
something
same
like
of
this,
yeah, the capacity should be minimum of the edge itself, or so any incoming edges, not the upcoming.
so how do
If we
you okay, so sorry.
So okay, for me, I updated all the incoming edges for each vertices.
Okay, so let's say I have this as 3, this is 3, this is 5, this is 3, this is 1.
Yeah.
How do you disperse the two incoming 3s into this 5?
Yeah. Okay. So yeah, you are true. So it's not a parallel. Yeah. Oh, yeah. Yeah. Okay.
Yeah.
What
If
I
you have
have
one
made, I
incoming
made.
edge and one outgoing edge, sure, you could just
You're
adjust
very
those
true.
edges, but there's no way to encode that on both edges into the 5 because yeah. Okay.
Thank you very much. Yeah.
No problem. Amsato?
So I just want to clarify something. I think I was confused because from the lectures, it is the flow in has to be equal to the flow out, right? Not the capacity in has to be equal to the capacity out.
Right. The flow in has to be equal to the flow out. Correct.
Okay. Thank you.
It would be a very boring problem if the capacity in has to equal to capacity out, because then you would just have the same capacity from beginning to end, and your minimum flow would just be immediately known coming out of S.
Yeah, that makes sense. I got confused.
Yeah, no problem. Mahmoud?
Yeah, Joves, sorry, I got disconnected mid your explanation, but I think I gathered it, so I just want to confirm my understanding. We convert each of the vertices into two vertices, V in, V out, and then just have the edge between them be the capacity of that vertex, and then run Edmonds Carp, and that should give us the answer to our flow problem.
Yep, correct.
Okay, thank you.
Yep. Problem. All right, so the next problem is 7.19. Oh, okay. So this one is verifying max flow. I'm just going to paste the whole solution because I think it's easier to talk about that way. So someone presents you with a solution to max flow problem on certain work. Give a linear time algorithm to determine whether the solution does indeed give a max flow. This is an excellent example of when we are moving into the NP complete topic. In some cases, for problems, the verification of a correct solution is easier or faster than solving the problem. And that's a good thing to keep in mind. The verification of a solution can actually, in some cases, take longer than solving a problem. That's an interesting one. I don't think we get into that, but I like the thought of verifying a solution might be harder than solving it. Think about that, but that's sort of out of scope. But in this case, the verification of whether a solution is the max flow is faster than computing the max flow, and this is how we do it. So first of all, we're going to verify the edge capacity constraints are met. So when you're giving a solution, it might break the rules of a max flow. It might not be the max flow. So we have to do all the things to verify all the different requirements, right? So first we verify each edge capacity constraint are met. So for each flow, verify that it is less than equal to the capacity of those of the capacities we're given, and make sure that it's over 0. Okay, so that's that one. Second, we verify that the flow into and out of V is conserved. So for every vertex, other than the source and sink, we verify that the sum of the flow coming into V is equal to the sum of the flow coming out of V. Okay. And then finally, we verify that the flow is actually a maximum flow. How do we do that? Well, we create the residual graph. Okay. So we take the capacity, the flow in the graph, and we create the residual graph, and we get back some residual graph, right? Then we run BFS on it and verify that T cannot be reached, right? Because that is the step for which we say that the flow has been maximized and we can no longer find flow, is to run BFS on the residual graph. So we do just that. And so if we cannot reach T, then there's no more flow, and then we're good. Okay. The correctness is that steps 1 and 2 verify each property of a valid flow. So those are just by definition. And step 3 verifies that the max flow by making sure that the residual network has no path from S to T, because that's why the max flow algorithm ends. Okay. And so to verify edge capacity is all of M. To verify the flow into and out of V is conserved is all of N plus M. And to verify that F is maximum flow is BFS, which is O of N plus M. And so this is linear time. The overall runtime is O of N plus M. Okay. Bing, question?
Hey, Joves, I'm a little confused on the step 2. When you're verifying the incoming and outgoing flows are equal, like the outgoing one is fairly simple to sum. How does the incoming one work?
Well, you have all the flows, right? And your flows are given in such a way that's like,
So I'm talking about the edges, right? So how do you identify the edges to sum up which edges flows? That's the part I'm.
Well, you don't have to. So you read the flow, your flow function or whatever, your flow array or function, whatever you want to call it, has the edges in. It'll be in the form of UV f of XV, right? So f of GV. So you just read this entire function or array, and everything that ends in V is the incoming flow to V.
Oh, you're saying the flow structure itself, the assignment structure, is something we can iterate through. And then we just need to check when the second vertex is the incoming. Okay, okay, that makes sense. Okay. I was like, if you have to go through every edge to filter, then it's not going to be it's not going to be linear time then. Okay, thank you.
Yep. Okay. And then so that's up to you. Okay. Jafar?
Yep. Sorry, but the flow you are saying it is UV, because in the algorithm that we have, the black boxes, it's only a list of edges. So what I have understood is that a flow It will be, for example, it's a list. The first item will correspond to H1, the second item corresponds to H2, third item H3, and this is corresponding to the list of E that we have of the graph. It's very critical because if I don't understand this, then
hold on. Yeah, I mean, it says it's a list of edges. Edges are represented by the two endpoints. So like it's kind of abstract on how you want to consider it, but you have access to what edge that flow correspond to, and you know what the endpoints of those of that flow is.
Mhm. Okay, understood. It's still doable if we consider that it is the first one will correspond the edge E1, which will be corresponding to the one in the list of edges, so it's fine. My second question will be building the flow, the residential flow for F. Here we will build it based on this F, so on this flow that we are given.
Yes, the flow
Okay,
that you're
understood.
given. Yep.
Okay,
Yep.
understood. Thank you.
All right. Next problem, 721. Oh, this is the critical edge question. So I think I misunderstood what the student was asking. So hopefully I get it right when we talk about it. So the question asks, an edge of a float network is called critical if decreasing the capacity of this edge results in a decrease in the maximum flow. You have an efficient algorithm that finds a critical edge in the algorithm. So I took this question as finding all critical edges. I suppose if you only wanted to find one critical edge, the easiest way would be to run one of your max flow algorithms like Emmons-Karp, and then like the student suggests, we look at our FT cut, which you can identify after you look at the residual network, and then any saturated edge that crosses that cut would be considered a critical edge, right? Because your min cut, which is identified as a possible as a min cut, once it's identified, you can find all your critical edges across it. Now the question is, what if I wanted to identify all the critical edges, or if I wanted to identify a critical edge that's not part of the min cut? Because you can have multiple min cuts. And it turns out trying to find one critical edge, not by using the min cut theorem, is just as fast as finding all the critical edges. So that's what I did. So apologies to the student who asked the question. I think I misunderstood what you were asking. If you wanted to identify a single critical edge, yes, find the min cut using Emmons-Karp and then finding a saturated edge across that cut. Now, what's interesting about that is that even though finding that critical edge across the min cut is fast, once you have your max flow, you're still you still have to run Emmons-Karp, and so it's still not a very fast algorithm. And so the process to finding all the min cuts, all the critical edges, is actually faster than running Emmons-Karp. And therefore, once you run Emmons-Karp, you can run a series of steps to find all the critical edges. So I will present my algorithm, and then we will talk about it. And it is going to feel like it's kind of brute force. And it kind of is, simply because Emmons-Karp is such a slow algorithm. So we can get away with doing a lot as long as we're under the Emmons-Karp runtime. So we're going to run Emmons-Karp, and we're going to get back our residual network, or get back our flow. And then we're going to build our residual network. And then for each edge, that is saturated, so each edge such that the flow is equal to capacity, we're just going to run BFS on the residual graph from U to see if V is reachable. Because if U can reach V, even if UV is saturated, that means that there is an alternative path from U to V, and we could have moved flow from one to the other, from one path to the other, and therefore UV, that edge, can actually be decreased without giving up the maximum flow. And so these are all our critical edges. We just run BFS on every edge, and on any edge that that U cannot reach V, it is a critical edge. So the residual graph is built after the max flow is found. If an edge is at capacity, then it is a candidate for a critical edge. So all critical edges must be considered saturated, right? Because if it's not at capacity or not saturated, then reducing the flow would not have affected the max flow because it wasn't saturated. Now for each candidate, we see if there's still a path from U to V. If there is, then we could avoid using UV and still push flow from U to V. If this is true, we can decrease the flow and the flow to the path that we found. We can redirect some of that flow. So UV is not a critical edge. The runtime is O of n m squared. Creating the residual network is O of n plus m. Now for each edge, which we run PFS, it's O of m times n plus m, which gives us O of nm plus m squared, which ends up being dominated by the O of nm squared of Edmonds carp, so it's okay. And that is my algorithm for finding all critical edges. Mahmoud?
Hi, Joves. I remember in prior office hours you said do not run BFS on every node.
Right.
But this feels like we're running BFS on potentially every node. So
right.
what's the deal?
Right. Do not run BFS from every node or on every edge if that is the start of your algorithm. But if you have to run one of the really slow algorithms, such as for image carp, such as for Warshall, those are like OOV cubed, O of m squared. Running BFS from every vertex may not be that bad, as long as you're not going over the runtime of your black box. Now, there could exist an algorithm that's faster than this. That very much could be possible. And I haven't really thought about it, but I guess I should. But if there is an algorithm that is faster than this, it doesn't matter because I have to run mn carps anyway. But if the question was, okay, you are given a max flow, mn carps has already run, you're given the max flow, determine which edges are critical edges, I might have to think a little bit harder on that to find a faster runtime. When I solve this problem, I just look at Emmons carp and go, as long as I'm faster than Emmons carp, it doesn't really matter what I do. And that's the solution I came up with.
So to summarize, running BFS on every edge after running Edmonds carp is essentially okay because the runtimes will just be capped at Edmonds carp.
Exactly. And my solution to this problem might actually be pretty slow, but because it's pretty slow in comparison to the black box I already have, I mean, it's not slow compared to the black box I already have to run, it's okay. If the question in turn was, given a max flow, find all the critical edges, I'd have to think about a better way to do this. And I probably can't think of it right now, but I might think about it.
That's fair. That's fair. And then there's a question in the chat from Coral. She said, I don't have a mic, but can someone ask why we chose EK rather than FF?
I don't see that the edges are integers, and without knowing that they're integers, I can't run FF. So I'm just going to run mx carp. That's all. That's it. If it was given as integers, I would probably run. I mean, it doesn't matter because I can't really argue which one's faster and which one's slower. I just know that 447 may not work with this problem because this problem may have non-integer capacities. That's all. I do believe I have a problem where I specifically have to run Emmons carp, which would be kind of. So this is 721. Okay, 722 calls out calls out the fact that these are integer capacities. So time to see some for Fulkerson. Oh, this problem I like a lot. And we actually do have to run for Fulkerson on this particular problem because it is optimal over Edmonds car. We'll see why. All right. In a particular network G whose edges have integer capacities, okay, very important that it has integer capacities. We already found the maximum flow from node S to node T. Great. However, we now find out that one of the capacity values we used was wrong for edge UV. We use CUV instead when it should have been CUV minus 1. Okay, so we oversaturated one of the edges by 1. This is unfortunate because the flow F uses that particular edge at full capacity, so it's saturated. We could redo the flow computation from scratch, but there's a faster way. Show how a new optimal flow can be computed in OOV plus E time. Okay. The way to think about this is that I have gone over one capacity, so it's 1C. Okay, I want to roll back that one capacity throughout my entire flow, and then recompute to see if I can increase my flow elsewhere. Okay, so you're basically just rolling back one step of your max flow. So you're going to take your residual network, or you're going to create it, okay? And then you're going to find a path in G from U to S. Okay, so let's show what this looks like. So you have some S here, and then you have some, flow network, whatever, and you hit V. And then you have this overcapacity edge from U to V. Or is it, wait, VU? What was it? U to V. Okay, sorry. This is a very ugly U. And this is V. And then you have some path, whatever, to T. Okay? Okay. So we are going to run on our residual network BFS from U to S. Now we know that there is going to be a path from U to S because U to V is saturated, right? And because U to V is saturated, we know that there has to be a bunch of back edges that leads from U to S. So we're going to run BFS going this way, okay? And then we're also going to run a BFS going from T to V, okay? So we know that there's a flow going from V to T, and therefore going backwards will give us the back edges to recover that path, okay? We're interested in the path that takes, okay? We take those paths and we decrease the flow and capacity of those edges by 1. Okay, so we roll back 1. And so we do everything here to roll back 1. We do everything here to roll back 1. And then we update this capacity. We lower this by 1. Okay. Update capacity. Right. And then we're going to create a new set of capacity. We're going to take out capacity, and we're going to subtract all the updated flows on our graph. So now our graph our new graph has a different capacity than our original graph, because if we use the capacity of the original graph, I don't know how many more rounds of for Fulkerson is going to run before it finds a new flow. But if I update all my capacities down to from the flow up to the new capacities, I know it can only run at most 1 round because I am 1 unit, possibly 1 unit too much. Therefore, rolling back 1 round of Fulkerson and then rerunning Fulkerson means on the new updated graph, it can only run 1 round. So we run Fulkerson on the updated capacity, add the outputted flow to the updated flows from before, and we return it. And so the correct answer is that we revert the final round of for focus n by finding a path from U to S and T to B using packages, decreasing the flow by 1 so that we do not oversaturate the edge that we are currently oversaturated. These paths using packages must exist because we know we sent flow from S to U and U to V and V to T, right? Because we know that U and V are saturated, there must have been some flow from S to U. And because U and V is saturated, there must have been some flow from V to T. And therefore, we know that there's a previous path that can exist. We didn't take all the updated values and run one more round of for focus. We know that we can most decrease our total capacity by -1, and so we need no more than one round of for focus to get our total capacity. And this is where our the using for focus makes it a little bit makes it cool to do our runtimes. Creating the residual graph is all Vim. Running BFS twice is all Vim. Again, this is all Vim plus N, but technically all of them because we know it's connected. Updating the flow on the path is all Vim. Running one round of for focus is all Vim because it's all of M times C. But because the capacity, we've left with one capacity, we know we only have one round. C equals 1 makes all of MC time all of M times C equal to all of M. So that is your runtime for focusing. And all of these all of them combined to be all of them total. So that is your linear runtime to do this. Okay. Questions, Mahmoud?
So I understand step 1 to step 4. We reduce the flow along the path from U to S, and then from T to V, we reduce the flow one more time. And then the edge, we reduce the flow and capacity by 1. But step 5 and 6, I don't understand.
Okay. So if we had left the capacity the way it was, and we just rerun for focus and you can't run a black box with a flow that already exists, right? I can't tell for focus and, oh, here is the flow I want you to start running with. Here, start up from where this flow again is, right? So if I had some capacity and I have some flow, I can't tell it to start from this flow. What I can do is I can decrease my capacity, all my capacities from the flow, and say, forget about all the flow I already created. Find out if I have any more flow with the updated capacity. That's why I now I can just tell it to start with 0 flow, start with this restricted or updated capacity, and I know you can only run round because at most I've only decreased your maximum flow by 1 unit. Therefore, your capacity, your maximum capacity of the entire max flow is 1. Can you find a path? The other thing you could have done was updated the residual graph, and then just run BFS to see if you could find a path. And if you have a path, then you update all the that path by 1, and that added to your original flow, and that's your new flow. Or you could just do what I just did. So either way works. But you can't run for focusing with a partial flow.
So we take the capacity and subtract it from the flow we just made using the residual, and then run for Fluckerson, which should at most change everything by at least 1.
At most 1, yes.
Sorry, at most 1. My apologies. And then that's that. Okay, I think I get it, but I'll rewatch. Thank you.
Yeah. And updating the capacity is a very sneaky and indirect way to tell full focusing to run from a partial flow. If I take all the partial flow away from the capacity, all it's doing is finding flow within the remaining capacity, which is basically saying, here's a partial flow, find the rest of the flow in this max flow. And that's what we have to do this because we can't use black boxes. And even if we could use black boxes, when you give full focus in a partial flow, it's not guaranteed to only run 1 round because it could possibly start switching the flow from different places. But if the capacity is 1 and I know my full focus and runtime is M times 1, then I know my my runtime is all times M. All of it. Right. Jafar?
Okay, thank you. Another time. So I have a specific question here because okay, I understood that you decreased the UV by one capacity, but why are we decreasing all the capacity of the flow?
Decrease the flow and capacity of EV by -1. We are, because like I said, I don't want to. If you don't reduce the capacity by the flow, you can't tell
Mhm.
4% to run a partial max flow algorithm. That's
Yeah,
basically what I'm
but
just.
maybe it will find another max flow for the same value, but without going from U to V. And if you reduce that by
Yeah.
one, then it may encounter that it will not be able to find this max flow anymore.
Well, I have to reduce the capacity because of E, because E is the wrong capacity. Its actual capacity is -1.
It's only from U to V.
Right, and that's what I did.
Ah, you are not updating the capacities from S to U?
S to U. Where do I say that?
Ah, you are updating the flow.
Yes.
So why
Because
are
I
you
have to
updating the
update
flow if you are rerunning FF?
because S to U right here. If this is one too many from U to V, then S to U is also one too many. And if U to V is one too many, then V to T is also one too many. So I need to subtract flow to roll back one round, and then tell 4%, hey, could you have found a different path to add that one capacity back? But in order to get it back to a valid state of my my correct capacity, I have to roll back a flow along this entire path.
Mm-hmm.
Right? Like if this is 7, and it should have been 6, the capacity from S to U through various places is also going to be 7, and then from V to T, it's also going to be 7.
Yes.
Right? Right. So if I subtract this to be 6, I also have to make this all 6s. Now, there's a potential that another path here could in fact give us 7, but I don't know. I'm going to run one more round of 4Focus and do that. But before I even do that, I have to correct my capacities to make sure everything's correct.
Yeah, but you are not sending those values to Fort Ferguson.
I know I can't. I can't
You
send.
cannot. So why are you decreasing them if you are not sending them to him? You are decreasing
Because
the
I'm sending.
capacities. I understood. I understood that you decreased the capacities.
Right. Okay. So you
Yeah.
understood. Okay. So, okay. If this capacity, okay. Okay. So I found a flow that sends 7 flow all the way from S to T.
Yes.
We agreed that 7 is our max, right?
Yes.
Okay. A and B is the wrong capacity. Okay.
Okay.
So now I am going to update this, and I'm going to say this is actually 6. Okay.
Mm-hmm.
Now I need to make this 6 out of 6, right?
Yes.
Okay. We agree to that. Now, I'm saying my claim is that I also have to make this 6 out of 7 and this 6 out of 7. Because I can't tell for focus, and here is a updated flow, send one down through here to get me to 7 out of 7. I have to encode into my capacity in some way to get for focus and to send one more unit of flow from S to T. If I don't update my my flow, what capacity am I sending to for focus? Right? I can't send the original capacity. If I send the original capacity, it's just going to rerun full focus in from scratch. I don't want that, right? If I don't update the flow and I send just the capacity minus flow, I'm going to send it 0, 7, 7, 7, 0. And that's no good because it's going to assume I can't send anything from S to T at all, right? So what I need to do is I need to first roll back that one flow, right? Because that now is a valid flow. And now I go, okay, what is my capacity that I want to send for focus in? Well, 7 minus 6 is 1. This has 7 flow. This has 7 flow. This has 7 flow. This has 1 flow. 6 minus 6 is 0 flow. Now, for focus in can take a look at this capacity and go, I can send one round of flow going from S to A to C, C to D, D to B, B to T. And what is that flow? It's the one of that capacity that I've updated. So now I
Understood.
send one
Okay.
flow all the way through. I add this capacity to my I add this capacity. So right, this is one capacity, this is one capacity, one capacity, one capacity, one capacity. I take that, I add it to the fixed flow that I have, and I end up with, and I'm so sorry for how messy this is. This ends up being 1 plus 7, 1 plus 6 is 7, and then I send one this way, one this way, one this way, and this is 7 again, and this right here is 6.
Understood.
So
Yes,
7,
understood.
6, 7, 1, 1, 1. And that gives me the corrected max flow. I mean, it gives me the same max flow, but it gives me the corrected flow of all my entire network.
Okay, thank you. And if we are making the capacity from A to B plus 1, so instead of 7, we make it 8.
No, because it's 0 right now.
No. I'm saying if the question was from A to B, it should be 8 instead of 7 of 6. So plus 1, not minus 1.
Why would it be plus 1?
I'm saying if it was the exercise was like that. So if they are telling us from scratch, so instead of E minus 1, it's E plus 1.
Oh, at that case, I would just run. I could just update all the capacities and run one round of. You can either run one round of for focusing by updating that capacity and taking
Yeah,
capacity
so we
minus the
don't,
flow.
but we don't want to go back and forth. So it's only we update this capacity and send it to for focusing.
Yeah. Or the other thing that you can do is just run, build a residual graph, update one of the edges, run BFS. Is there a path? If yes, then augment the entire path with 1, and then that's your new flow. I could have done it that way for this problem as well. I just like the idea of running for focus on one more round and tricking it to do one single round.
Understood. Okay. Thank you.
Yep, no problem. Shanek?
Hello, Jobs. Quick question. So here, so referring back to the previous question, would we say that AB is not a critical edge, right?
AB would not be a critical edge. Yeah.
And if you were to make a min ST cut here, can you show like how that would look like in this case?
I will try. Right. So we have S A B, what's it, T? K. Okay. And we said that this was Where is my min ST cut? So the residual graph for this would be
So there will be no edge S to A, no edge A to B, no edge B to T,
yeah,
right?
I think my min ST cut would be right here.
Just that. So
And
how many ST
yeah,
cuts, how many min ST cuts are here? Because you referred that there can be multiple cuts. I'm just trying to wrap my head around
so that would
what.
be one min ST cut. This would be one min ST cut. So I have two critical edges.
So the edge A to B, there would be no min ST cut going through that one, right?
No. Yeah, my ST cuts are where my max flow is cannot be raised.
I feel couldn't you cut through A, B, and DB? Just cut through both of those, and that would be a min cut, or it has to be
A, D, and B. Wait, sorry, say that again.
A, B, B, D. Just a line through those. Wouldn't that be a min cut? Because you have 7 going in and 7 going out. Isn't that a min cut?
Right here.
Yeah, like that.
Right here.
Yeah. Wouldn't that be a min cut?
No, the total capacity coming from the left side to the right side is this 6 capacity plus this 7 capacity. That's 13 capacity. I know my capacity, my max flow is 7, so that 13 capacity is not a min cut.
It's capacity, not flow. Sorry, my bad. Okay.
Right.
Sorry.
I mean, your min flow is always going to be 7, no matter what, right? And so you can make all sorts of cuts and claim it's a min cut if it was based on flow. It's only based on capacity.
Right. Thank you.
Yep. Bing?
Sorry, I had one more question, if that's okay.
Okay. Yeah.
Is finding all min ST cuts a polynomially solvable problem? Like, would we get a question that says find all min ST cuts?
I don't know if you would get that question, but finding all min ST cuts, I believe, should be doable. Let's find out. I mean, I'm not going to write a solution, but
No. Okay, got it. And then in your model solution, you showed that the path augmentation is O of M. Is it not O of N or in the solution?
one second. Finding all minimum ST cuts in the flow networks is more complex problem than finding a single minimum cut. What is the runtime? Oh wow, finding all minimum cuts, explicitly enumerating them, can be exponential in V, as the number of minimum cuts can be exponential. But finding all edges that belong to some minimum cut can be done in polynomial time. Interesting. Okay, sorry, what was the question?
Sorry, no, thank you. In the solution for the step where we want to update the flow along the path,
Yeah.
I was curious why that is O of M. Because I thought that the previous array would have like maximum n vertices. Or
that is true. I think either is fine. You can say O of N, O of M. I just like to work with M when it's edges, but yeah, O and
Okay, got it. Okay, thank you.
yeah. Yeah, let's go with O of N. I like that more. That makes more sense to me too. Updating the flow on the path is O of N. Yeah. So let's see. M N. All right. Bing.
Hey, Jovis. I'm going back to the critical path thing. I've been spending quite a bit of time trying to differentiating the properties of that in comparison to bottleneck link, which is also another concept in DPV. They're very similar, but still different. Am I correct to say are all bottleneck links, bottleneck edges also critical edges, or the other way around?
Pretty sure we had a bottleneck question. Which okay, so 7.7. So a bottleneck edge, if increase in the capacity result in an increase in maximum flow.
Right. Can we say that bottleneck edges, no, bottleneck edges always critical edges, but not the other way?
Okay. So not all critical edges are bottleneck edges for sure, right? We can get an example of that.
Right.
I'll think about
right.
the second thing. Okay. So if I had right, these are both critical edges, but neither of them are bottleneck edges.
Suppose we only have these two edges, 3 nodes, right?
Right. So those are not all critical edges are bottleneck edges.
Right,
Are
right.
bottleneck edges the same as critical edges? Let me think.
So my thought process, if increasing the capacity will always increase the max flow, that means it's already saturated, right?
Mm-hmm.
And wouldn't decreasing that capacity cause it to decrease the flow? Because if there was an alternative path,
No,
then there was.
so not all saturated edges are critical edges.
That's true, but if you increase the capacity, always results in an increase of the max flow of the network. Doesn't that mean you reduce that will also cause that to decrease?
Yeah, I think that's true. I think all bottle edges are critical edges. All critical edges are saturated edges, but the other direction is not true. Not all saturated edges are critical edges, and not all critical edges are bottleneck edges.
Okay, thank you.
Yep. Timothy?
Yeah, hi. My question is related, I guess, just in general. So this was an example of a problem where we used EK. Is there like general guidelines? Because my impression, sort of watching, going through the lectures, was that we should use EK over FF, right?
If a problem presents itself and you can use either, you can use either. It won't be like, oh, you use if you can use either and the runtime it cannot be determined based on the graph. Why if one is faster than another, then you can just use either. If the graph is presented in such a way that you don't you don't know if the capacities are integers or not, you should use EK because FF doesn't work with non-integer capacities. So then the second part is if one is going to be O of MC and the other one is going to be O of NM squared, right? you're basically comparing C to NM, right? So if you know that C is larger than NM, then EK is faster. If you know that NM is bigger than C, then you know that FF is faster. So if you can determine the relationship between the two, you can choose between the two. If you know that the graph if you don't know if the graph has integers or not, then you have to use EK to be safe. And if you don't know, if you know that the capacities are integers, which would be odd for us to give to you without a reason. If you know the capacity of the integers and you don't know the relationship between capacity and NM, then you can choose either.
Okay. And this was just like a special case where we knew exactly that the capacity was going to be like 1 because we were doing like 1 additional round, right?
Yeah.
Okay.
How mean would it be for me to create a problem that specifically says integer capacity, but I give enough tricky details into that causes this relationship to happen? And so even though it's integer capacities, you are expected to use EK. I think that would be kind of mean. I don't think we would come up with a problem like that. But that would be the only situation where you see integer capacity and it goes, oh, I still need to use EK. How would you determine the capacity relationship to NM without returning the algo first? If NM is severely constrained, or if C is severely constrained, like in this case, I know that C is 1. It's a special situation, and I know that NM is going to be bigger than C, which is why I chose full Fulkerson. You generally can't if it's a general Maxwell problem, but if some indication of the problem tells you that one or the other is severely constrained, then that is something you can do. Mahmoud?
If we had chosen to run Edmund Karp, would we have been penalized if this was like a homework or like a exam question?
I think so. I think there's enough information here, especially saying that it's integer capacity, especially saying that the capacity is oversaturated by 1, that you should be able to claim that full Fulkerson is O of M, and you don't know what the size of the graph is. So the runtime of Edmund's card will be O of NM squared. And in this case, it is definitive that full Fulkerson is faster.
Understood. Thank you.
Yep. All right, I have gone an hour and 10 minutes over the time I thought it would take to cover this. I should just stop giving estimates on how long I think it'll be to cover everything. I'm not going to go over the next problem. Like I said, any problem that is marked as like extra hard, I don't bother going over because I think it's outside of the scope of what you will need to know for the exam. And for you to really get any satisfaction out of solving that problem, you ought to solve it yourself. Okay. Have I even solved that problem? Which problem is that? 7.24? I don't think I've ever attempted it. I might tonight just for fun. All right, Jafar?
Yep. So before closing, I have a question. So if we are to give the best algorithm to get the minimum cut property, okay, minimum ST cut.
Okay.
How to find the minimum ST cut in a graph, for example.
Yep.
What we should do.
To identify a single ST cut?
The minimum ST cut, yes. A single minimum ST
To
cut.
identify a single minimum. So you run Edmund's cart, which gives you
Yes.
your residual graph. Once you have your residual graph, you see what all the vertices that S can still reach. So you run BFS or BFS from S. You get all the vertices that S can reach. You take those vertices plus S, and you say that is your one side of your cut. All the other vertices that S cannot reach is the other side of your cut. Then you check all the edges that go from your S cut to your non-S cut, and those edges, outgoing edges, would be part of your min cut. And then you add up the capacity of all of those edges, because those edges will all be saturated. The reason you can't reach beyond those edges is because they're saturated, and so that would be your minimum, one of your minimum ST cuts, and adding up those capacities is your max flow.
Yeah, and this is basically O of n square m, n square.
It was m squared because you're upper
Yeah.
bounded by the run of m
And
squared.
if you already have the max flow and we need to get the best way of getting the minimum capacity,
Then it's BFS from S, and that's all of n plus m.
oh, okay, okay, thank you.
No. In general, when you're doing graph problems, if you reach a O of n plus m solution on one of the problems, you're pretty good. Like that's linear time. I can't think of any like non-trivial problem that would be faster than O of n plus m. So if you get O of n plus m, you should be pretty happy.
Mm-hmm.
Mahmoud?
Yeah, so just going off of the thing you just said with Jafar, because I kind of got a little lost. If we have the maximum, we create the residual. The minimum cut is the area at which we can separate the graph, the residual graph.
Yes.
And that's always that's always to be the case. It's a safe bet that the residual graph where you cannot reach t, those edges you can cut down the middle, and it should always be a minimum cut.
So two of your minimum cuts are really easy to identify. Your first minimum cut is all vertices that S can reach on one side and all other vertices on the other side. That is one min cut. The other really easy to identify min cut is to reverse your residual graph, run BFS from T, and all vertices that T can reach in the reverse graph is also all the vertices that can reach T in the original graph, the original residual graph. And that is your second obvious minimum cut. So right in this case, my minimum cut is here and my minimum cut is here. Okay. Anything in between those two minimum cuts, there are additional work to be done, and finding all of those minimum cuts is a very hard problem.
Okay, so it is safe to assume that the minimum cut is the area which S cannot reach T in the residual. That area there is the
not that S cannot reach, just the vertices that S cannot reach is on the other side of the cut. There can exist a bunch of vertices in the middle that S cannot reach and also can reach T, simply because both sides of that area are minimum cuts.
Oh, so it's
if an
all of
area,
sorry, go ahead.
Yeah, if an area of the graph in the residual graph is between two minimum cuts, S can't reach it, it also can't reach T, which is why you have to be careful on how you want to present this. A simple minimum cut, ST minimum cut that you want to identify is to run BFS from S, and all vertices S can reach is on one side of the cut, and all vertices S cannot reach is on the other side of the cut. It doesn't make sense to state it as vertices, what area that S can't reach T. Like that, S is not trying to reach T. S is trying to reach all the vertices that it can, and that is one side of the cut.
So everything that S can reach in the residual is a minimum cut.
Is one side of the minimum cut. A minimum cut has two sides to it, or two subsets to it. So everything S can reach using BFS is one subset of the minimum cut, and everything that S cannot reach using BFS is the other side of the minimum cut. So that is to identify a single minimum cut. Yep.
Okay. So we just find the ones that S can reach using the distance of BFS. Those are one side,
Yes.
and the other ones are the other side. Understood.
Right. And that defines one cut. Yeah.
Okay.
One cut cannot be like multiple things. It's two things exactly. Two subsets of vertices exactly.
There has to be two sides to it. Of course. Okay, that makes sense. And it's the same thing when you flip the graph and run from T.
Yeah, that is the other minimum cut. Now, if from T and S you do this and you end up with the same cut, does that mean it only has one min cut? I believe that's true. I can't be sure. I'd have to think about it. But doing the two things could identify a single cut. That sounds to me like it would only have one specific minimum cut, but I have to think about it. Don't take my word for it. That's just what I kind of thinking out loud right now.
I'm good with the run from S, run from T idea. I'm okay with that. Thank you.
Okay. Yep. Tyler?
I'm a little lost on minimum cuts versus critical edges. I'm just curious, using that same pattern you did for minimum cut, could we also look at all the edges in S? And let's say S is all the edges reachable from, let's say A. I'm doing this bad. Let's start with S is the starting vertex. R is the set of vertices reachable from S. And then we take all other vertices and put them in Q. And then if we took every edge and looked over that cut, if any of them have maximum capacity, we would have a critical edge.
So all edges that crosses a minimum cut going from one side to they're going from the S side to the non-S side, are going to be saturated. And those saturated edges are going to be critical edges.
Okay, so all of those edges would be critical then.
Yes.
So
because there's no way there's all those edges that combine to be if all those edges combine to be a minimum cut, that means that there's no other edges along that cut that could have flow. And so if you were to decrease the flow of one of those edges, there would be no place along that cut to divert that flow, meaning that that edge that crossed the minimum cut is a critical edges. And that turns out to be true for all the edges that cross a minimum cut. And so every edge that crosses the minimum cut is a critical edge.
In that case, for the, don't know the number, 7.12 maybe it was, that you did with the kind of BFS from every edge, we could have also done BFS on the residual and then separated it and gone through and said, hey, for every edge, is U part of R or
so
not
my
R?
algorithm that I presented finds every critical edge. If I was to use the residual graph and run BFS and just say that'll only identify some critical edges, at least one, but it doesn't identify all the critical edges.
Okay.
Yeah, and this is actually interesting because I just told you that all edges going across a minimum cut is a critical edge. Therefore, identifying all the critical edges identifies where all identifies all the edges that would participate in a min cut. But the combinations of which edges create a min cut can be exponential, or a combinatorics, and therefore finding all min cuts is not a simple problem. But finding all edges that would participate in a min cut is a polynomial time problem. But you don't really have to worry about that. You don't have to worry about that for this exam. That's just interesting things that to me. All right. Any other questions about the topics, the exam? I know it's getting late, so feel free to not ask questions if you don't have any. Okay, great. Well, good luck on your exam. I will be rooting for you. I hope you all ace the exam and don't have to think about graphs for much longer. Good luck, everybody.
Thank you.
Thanks, Joves.
Thank you, Joves.
Thank you.